guest today.
Yes. I would like to welcome everyone once again on behalf of Center for Climate Change and Water Research, Suresh Gyan Vihar University, Jaipur, Rajasthan, on the 8th day of the Summer Winter School in Geospatial Science and Technology, Level 1 program sponsored by DST NGP. Now let me introduce to our first speaker of the 8, Dr. Varun Narayan Mishra sir. Dr. Varun Narayan Mishra sir is working as an assistant professor at Center for Climate Change and Water Research, Suresh Yanviha University, Jaipur, India. He did his PhD from Department of Physics, Indian Institute of Technology, BHU. Before that, he received his MTech degree in remote sensing from Birla Institute of Technology, Mishra, Ranchi, and after completing MSc degree in physics. Previously, he worked as a junior research fellow at Center for the Study of Regional Development, JNU, New Delhi, under DST-funded research project. His main research interests are digital image processing and analysis, microwave remote sensing, machine learning techniques, land use land cover mapping, urban growth analysis and modeling, urban climate, glacier mapping and monitoring. He has published around 40 research papers in various reputed journals in national and international peer-reviewed journals. He also authored many edited books, reference books, and book chapters. He is also the reviewer of many international journals of repute, such as GeoCarto International, Journal of Earth System Sciences, Advances in Space Research, Arabian Journal of Geosciences, and the Journal of Urban Management, etc. So we are very delighted to have you here, and I would like to welcome you to start with your session. Thank you.
Okay, thank you, Upasana. Thanks a lot for introduction. Very good morning to all the participants who are present here. I'm going to first share my screen, then I will start my today's talk. I think my screen is visible now.
Yes, sir. Yes, sir. Please.
Okay. So once again, a very good morning to all of you, all the participants who joined this session. And myself, Dr. Varun Mishra, as discussed, as already introduced by Ms. Upasana. Today, I'm going to discuss about some physical basis of remote sensing. Till now, most of the lectures are focusing on GIS and spatial analysis and GPS and other technologies. So today I am going to discuss about something about remote sensing. All of you are must aware with the remote sensing term, but today I am going to see and I am going to describe about some physical basis, some physics behind remote sensing processes. So before starting, as we know that we do remote sensing every time. Means in most of the cases, whatever we visualize around ourselves, it's a kind of remote sensing. So remote sensing, we do it many times, or you can say daily we do remote sensing. Okay. And most of the processes, or you can say most of the things around ourselves that senses by the human, and the human gathers the information about external world, and most of the information what we gather about the real world, it's a kind of signal. Okay, the signal may be different types of waves or pulses, and whatever the information or whatever the signal we receive, it may be some kind of reflected energy, it may be some kind of emitted energy, and basically we use two different processes to gather the information actively or passively. So remote sensing is not nothing much. It's more than a technology. Means whatever we see around ourselves is a kind of remote sensing, and whatever information we gather, it's a kind of emitted energy or reflected energy in terms of infrared, microwave, or other kind of optical regions. Okay. So now moving to next slide. So remote sensing is very well aware with all of you. Remote sensing is a kind of earth observation technology. And when we talk about the remote sensing process, so remote sensing can also be considered as a teledetection. Means we observe the earth surface features without having any physical contact. And whatever the information or whatever the images we gather through remote sensing process is more than a picture. Okay, that in one of the lecture it is already described that what is the difference between picture and image. So whatever the information we gather through remote sensing or different sensors, it's more than a picture. Okay, and the remote sensing is looking into the earth object without any physical contact. So whatever the satellites is revolving around the earth is a kind of, you can say, artificial eyes. Means we are observing the earth without any physical contact, without having any physical touch with the objects. So remote sensing can be considered as an artificial eyes in the space through which we observe the earth surface, we monitor the changes in different natural resources or different disasters and other kind of human activities and man-made activities, or you can say the natural activities can be observed through the remote sensing process. So this is very commonly used process for remote sensing. This kind of remote sensing process, all of you are very well aware with remote sensing process. In the remote sensing process, we should have an energy source, and sun is a natural energy source, and whatever the energy that is coming from the sun in the form of electromagnetic radiation, when it reaches to the earth surface or when it interacts with the target on the earth surface, there are three kinds of mechanism: either it will be reflected or absorbed or transmitted. So the energy which is reflected from the earth surface is gathered by the sensor, and then that information will be sent to the processing station. They process the information in terms of images, different types of data sets, and we analyze the data sets for different applications. So this is a very common process of remote sensing. Okay, so remote sensing method tries to answer four basic questions. When we use remote sensing, so it is used to answer some basic questions: that what kind of feature is there, what is the extent and shape of the feature. It may be any kind of natural feature or man-made feature, and it can also be used for monitoring the changes over the earth surface. In case of forest, in case of water bodies or glaciers, different changes can also be observed in the remote sensing process. And also it can help us to identify different types of objects, or what are the landscape or different characteristics of the landscape on the earth surface. So remote sensing method try to answer four basic questions. Most of the things you already know about the remote sensing. So there is a very important difference between remote sensing and proximal sensing. We generally use remote sensing term that makes the measurement and collects the data about any object. It may be natural object or man-made object without any physical contact. That is a remote sensing. But the proximal sensing is another kind of process that includes the direct contact with the target. So there may be the two types of sensing processes. One is remote and one is proximal. So generally, we use remote sensing process for getting the information without any physical contact. But if we gather the information through some direct contact or having some physical contact with the object or targets, that is known as proximal sensing. So that is the difference between a remote sensing process and proximal sensing. Generally, in remote sensing process, we use electromagnetic radiation as a source of energy that interact with the object on the earth surface, and the sensor gather the information coming from the target on the earth surface. Okay, so this is an example. Means if we are going to measure a physical temperature of a human body or a person, so there may be the two ways to gather the information about the physical temperature of any human body. The proximate approach would be to place a thermometer on the body. Okay, if we want to measure the physical temperature of any person, then we use thermometer. It will be in the physical contact with the body, human body. That is a proximal sensing. And when we use remote sensing term, so remote sensing is a kind of process where we use some sensors to get the information, but we don't have any physical contact. We put the sensor at some distance from the human body or a person from which we are going to observe the temperature. So this is the best example to differentiate between the proximal sensing and remote sensing. And also in both of the cases, either we are going for the proximal sensing or remote sensing, in both the cases, our sensors should be calibrated. Calibration is very important. Whatever we observe, whatever we are going to observe, whether through proximate sensing or remote sensing, its response must be transformable into the good approximation of the actual temperature. Before measuring anything, our sensor should be calibrated to a reference point or to a reference value, so that the information or the temperature, in this case, what we gather, it can be considered as a approximation of the actual temperature of the body. Okay, so the calibration is very important. Most of the sensors, before launching, we should focus on the calibration. Calibration is important. Without calibration, without having good calibration process, we cannot say that our measurement is accurate. Whatever the sensor is getting, if it is accurate, then before that we should calibrate our sensor so that it can observe the accurate temperature or any kind of measurement without any physical contact through some processes. Okay, so these are some of the applications of remote sensing. You all are very well aware with these kind of applications of remote sensing. It can be used for remote processing, digitization, data extraction. We can also use remote sensing for pattern analysis. Surface modeling can also be done using remote sensing processes. We can also use remote sensing data sets for preparing the digital terrain models, dam extraction, land use land cover changes, land use land cover analysis, different types of other applications of remote sensing is there, and we use it for different applications. Okay, so in remote sensing, we collect the information without any physical contact, without having into the physical contact with the object. So whatever the process is involved in the remote sensing process, it is based on three different types of, you can say, the source of energy, whether it is reflected from the earth surface from the target, either emitted from the target on the earth surface, either backscattered radiation. That is a case of active remote sensing. So there are two types of remote sensing process. One is passive remote sensing, in which we generally measure the reflected solar radiation, and in some cases we measure the emitted solar radiation from the earth surface. And second type of remote sensing process is the active remote sensing process, in which we use the radar or lidar. That is a kind of artificial energy source. The sensor itself produces the energy. It will be sent towards the target on the earth surface, and it will be backscattered from the earth surface. So three different processes are involved in the remote sensing process: reflected radiation, emitted radiation, or in case of active remote sensing, we use the backscattered radiation to get the information about the earth surface. Okay, so this is the figure. This figure is showing three different processes for remote sensing, in which we see that here there are three types of remote sensing processes. One is the visible and reflected remote sensing process, that we generally call it as optical remote sensing. A passive remote sensing may be of two types, that is optical remote sensing, or you can say the thermal remote sensing. Okay, so in visible and reflected infrared remote sensing, the information can be gathered in terms of reflected energy from the target on the earth surface. Thermal infrared remote sensing is a kind of process in which the sensor gather the information that is in terms of emitted energy. The earth surface emits the energy, and that energy will be received by the sensor. These kind of sensors are known as thermal sensors or thermal infrared sensors. And third type of process is microwave remote sensing process, in which generally the sensor produces its own source of energy. The energy will be transmitted towards the target on the earth surface, and the backscattered energy is captured by the sensor. So there are differences between these three processes. Radiation source may be the different. In case of visible, there may be the sun as a radiation source. Then in thermal remote sensing, the emitted energy from the object is considered as a source of energy, and in microwave remote sensing, there may be the own source of energy that is produced by the sensor. And the visual is a kind of reflected energy. The thermal infrared is a kind of radiating energy or emitting energy from the earth surface. And microwave remote sensing is a kind of radiating as well as the reflecting energy. So passive remote sensing, active remote sensing. There are two types of remote sensing process, and you see the spectral radiance or whatever the energy is reflected from the target. It may be the highest energy in terms of reflected radiance coming from the target. Then emitted energy or the emitted radiance is a kind of energy that is emitted from the target. So its intensity is little bit less than the reflected radiation from the target. Okay, so depending on the object on the earth surface, we may have different types of energy. Either it will be reflected or emitted from the target. Okay, so generally in remote sensing, we collect the electromagnetic radiation. The solar radiation or the energy coming from the sun is a kind of electromagnetic radiation. So we generally collect the reflected energy, that is a electromagnetic radiation, and there may be the two different sources for producing the electromagnetic radiation. That may be the solar radiation, it's a natural energy source. Generally it is used for passive remote sensing. And artificial source is a kind of active remote sensing in which we use lidar and radar system to generate the artificial source of energy. So remote sensing is totally dependent on the measurement of electromagnetic radiation, or you can say the spectrum of the electromagnetic radiation. So it is very important to study the characteristics of electromagnetic radiation. What is the electromagnetic radiation? What are the characteristics of electromagnetic radiation? So the energy coming from the sun is a kind of electromagnetic radiation, or in short, we call it as a irradiance. Irradiance is the amount of energy coming from the sun, and that is reaching to the earth's surface. So the energy that is coming from the sun, it travels through the atmosphere and reaching to the earth's surface, and it passes the atmosphere. And when we talk about the electromagnetic radiation having two components, that is electric field and magnetic field. Any kind of electromagnetic radiation is having two components, that is the electric field and magnetic field. And the range of the electromagnetic radiation of different wavelengths and frequencies extends from the cosmic wave to the radio waves. As we know that electromagnetic radiation is having different wavelength intervals. These wavelength intervals are considered as the electromagnetic spectrum. That is divided into shorter wavelengths to the longer wavelengths, and the arrangement of different wavelength intervals is known as electromagnetic spectrum. Okay, and there are different properties of the electromagnetic radiation, or you can say the electromagnetic wave. Okay, so electromagnetic waves are the transverse in nature. It is different from the sound waves. Whatever the sound wave we use, that is a kind of longitudinal wave. It means there is not a fixed pattern of the propagation, whereas in terms of when we talk about the electromagnetic radiation, it's a kind of wave that follows a specific pattern, and the direction of the energy transfer follows the transverse wave propagation. Transverse wave propagation means the particles in the wave, the particles in the radiation vibrates perpendicular to the direction of the radiation. So the electromagnetic radiation is a kind of wave that is transverse in nature. It doesn't require any medium. It can travel through the space with the speed of light. Okay, and so electromagnetic radiation is also considered as a light. Light is a, you can say the radiation is a type of light source, and it travels with the speed of light. It doesn't require any medium. It can travel through the empty space throughout the universe. It can travel, and its nature is transverse. Transverse means the vibration of the particles in the electromagnetic radiation is the perpendicular to the direction of the energy. Okay, so the electromagnetic wave is having two components, as we already discussed that it is having electric field and magnetic field. So the electromagnetic radiation is having electric charged particles, electronically charged particles. Okay, so when these charged particles travels in the space, they create or they produce the magnetic field. So whatever the vibration is there in the particles, whatever the vibration in the electric field, or you can say electromagnetic radiation is having different very teeny particles. So these teeny particles are negatively charged, or you can say it's a kind of electrons. So when it moves, there may be the production of the magnetic field. So there are two components of any electromagnetic wave. It is having electrical field and magnetic field, and because of its propagation in the direction of the energy transfer, it travels with the speed of light, and that is the fastest entity in the universe. So you see here, the electric field and magnetic field both are perpendicular to each other, as we know that the electromagnetic waves are transverse in nature. So the vibration of particles will be in the perpendicular motion, and it also having perpendicular, or you can say it's perpendicular to the direction of the propagation of the wave, and the distance between two consecutive peaks or crest is known as the wavelength, and the number of waves passing through a unit time at a particular position is known as the frequency. The wavelength frequency is a very important property of the electromagnetic radiation or electromagnetic wave. So as we know that electric field changes because of the propagation, there may be the changes in the electric field. So because of the change in the electric field, there may also be change in the magnetic field. So the changes in the magnetic field, or with the increase in the electric field, because of the change in the magnetic field, the changing magnetic field causes the electric field to change. So both, you can say, the electric field and magnetic field both are perpendicular to each other, and both are affecting each other. If there is a change in the electric field, there may be the change in the magnetic field, or if there is a change in the magnetic field, it can also causes the change in the electric field. And because of this, there is a vibration, and this vibration results in terms of electromagnetic wave, in which the electric field and magnetic field passes through some space, passes through the space or travels through the space with perpendicular direction with the direction of the motion. Okay, so this is the way how we can see the spectrum. Electromagnetic spectrum, you can say it's a arrangement of different wavelength intervals. It is starting from the gamma rays, X rays, then ultraviolet, visible portion, which we see our through our eyes, then infrared, microwave, and radio waves. So the entire wavelength ranges is arranged from the shorter wavelength to the longer wavelengths. Starting from the gamma, it's a shorter wavelength, and when we move towards the radio waves, it's a longer wavelength. So the entire wavelengths or entire wavelength intervals are arranged in the sequence of the shorter wavelengths to the longer wavelengths, and this arrangement of the wavelength is known as electromagnetic spectrum. Okay, so when we see the electromagnetic spectrum, so the visible portion, whatever we see through our eyes, that is a visible portion of the electromagnetic spectrum. It is only having 2% of the entire spectrum or entire wavelength range of the electromagnetic radiation. Okay, but it is very important for remote sensing purpose, as well as it is very important because we can also see the visible portion of the electromagnetic spectrum, but it comprises only 2% of the entire spectrum. And most of the sensors that we use for remote sensing purpose, either it is a panchromatic sensor or black and white sensor, there may be the color film or infrared film, all these kind of techniques for remote sensing uses the visible portion of the electromagnetic spectrum. And there are some other sensors that uses the infrared portion of the spectrum, that will be very much useful for studying the vegetation and other features. So the electromagnetic spectrum is having different wavelength intervals, and for remote sensing purpose, we generally use visible portion, then infrared portion, and longer infrared portions, as well as the microwave portion of the electromagnetic radiation. So these are the measurements. These are the measurement units for the electromagnetic spectrum. Okay, we can measure the wavelength interval. As we know that electromagnetic spectrum is the arrangement of different wavelength intervals. So we can measure the wavelength intervals using different units. It may be measured in centimeter, millimeter, micrometer, nanometer, and angstrom. So these are the conversion units, means you can convert centimeter into meter, millimeter into meter, and micrometer, nanometer, angstrom. These are some of the units. You can use any of the unit to measure the wavelength interval, to measure the spectrum of the electromagnetic radiation. Generally, in remote sensing, we use micrometer, μm, and nanometer for identifying or for getting the range of that wavelength interval. Okay, so when we talk about the electromagnetic radiation, so electromagnetic radiation, as we know that electromagnetic radiation is having two components, that is electric field and magnetic field, and because of the change in the electric field and magnetic field, there may be the propagation of the electromagnetic wave. So first time the Maxwell was a scientist. First time he described this kind of mechanism. First time he described the process through which electromagnetic radiation propagates in the space through the changing electric field and magnetic field. And for that, Maxwell derived four basic equations that is very important for electromagnetism or electrodynamics. So, and most of the electromagnetic radiation, the study of electromagnetic radiation or the study of electromagnetism or different electrodynamic processes are based on the Maxwell equation. Maxwell uses different methods, different calculations to summarize its finding about the electric field and magnetic field when we talk about the electromagnetic radiation. So these are the basics of the electromagnetic radiation or electrodynamics. So apart from the Maxwell equation, there's a Gauss law that studies the change in the electric field. It studies the change in the electric field because of the change in the magnetic field. Then there is a law that states that there may be no magnetic field if there is no charge. Okay, if there is no electric charge, there is no electric field, so there may be there will be no magnetic field. And because of the change in the electric field, and this electric field produces because of the movement vibration of the charged particles. So the magnetic field produces because of the changing electric field, and this electric field changes because of the vibration of the electrons, and you can say the negatively charged particles. And the magnetic field is produced by an electric current, whatever the if you most are we know that when the charged particles or negatively charged particles or electron travels, it produces the magnetic field. That is, you can call it as a also you can call it electric current, that also having very important in the changing electric field. So most of the technologies used in the study of electric field or electromagnetism, they uses the Maxwell equation. Okay, so this is the way how the changing electric field produces a magnetic field. So you see here, this is a closed loop, means whatever the energy or you can say whatever the charged particles are there, when it passes, it works in the closed path. It's charged and it moves in the closed path. Because of this movement, there may be the production of the magnetic field, and because of the electric field and magnetic field, there may be the you can say electric current. Okay, so this can be described by the Ampere's law that relates the magnetic field around the current to the surface. Okay, so in order to describe the Ampere's law cannot matter which surface we choose, but because of the movement of the charged particles, because of the change in the electric field, there may be the production or there may be the creation of the magnetic field, and that magnetic field passes through the closed path around that medium, or you can say the movement of that charged particles. Okay, so because of this movement in terms of electric field and magnetic field, that there may be the production of the electromagnetic waves. These electromagnetic waves causes these electric fields are produced because of the changing electric field that produces magnetic field, and a changing magnetic field produces an electric field. Okay, so because of the change in the electric field and magnetic field, it propagates with the speed of light, and electric field, magnetic field, and also the propagation of that wave. These three are perpendicular to each other, means they moves in a way so that it can have the perpendicular direction with each other. So that is known as electromagnetic wave. So this is the way how these charged particles oscillates, and because of their oscillation, because of their movement, there may be the production of the electromagnetic waves through you see, this is the way how the electric or electromagnetic waves travels or oscillates in the medium. Okay, this is another way how it is having different direction, means when the charged particles produces the magnetic field, so charge, electric field and magnetic field, they are also perpendicular to each other, and they propagates in the direction, and in the direction is also perpendicular to the electric field and magnetic field, and through which you can say the direction of the wave travels in a way that electric field, magnetic field, and the direction or the propagation of the wave, all these three components are perpendicular to each other. Okay, so this is the way how the electric and magnetic waves are perpendicular to each other, and also they are perpendicular to the direction of propagation, and that is the way how electromagnetic wave travels. So this electromagnetic wave generates the electromagnetic radiation. Before going for the study of electromagnetic radiation, it is very important to see what is the electromagnetic waves, and what is the process behind the generation of the electromagnetic waves. Okay, and Maxwell also calculated the speed of this propagation. Whatever the electromagnetic wave is propagating, it is having the speed of light, but the speed of light is, this formula will tell us that the electromagnetic radiation is a kind of light source. So here two term is there, epsilon zero. This is the epsilon zero and mu zero. Epsilon zero is the permittivity and mu zero is the permeability. These two terms are very important. Based on these two terms, Maxwell calculated that the speed of electromagnetic wave is the speed of light. Okay, and epsilon zero is the permittivity. It's a total amount of electric charge, and permeability is the total amount of magnetic charge. Electric charge and magnetic charge, and these are the constants, and these constants are used to calculate the speed of light by Maxwell. It is very lengthy calculation. It's a very lengthy process to calculate the speed of the electromagnetic wave. Okay, so it was done by Maxwell proves that the electromagnetic radiation is a kind of light, or you can say electromagnetic radiation is a form of the light, which is the fastest entity in the universe. Okay, so this is also we considered as the speed of light in the vacuum, because epsilon zero, this is the epsilon zero and mu zero, these two terms are the kind of constant that is measured for the empty space for the vacuum, and using this terms we can easily calculate the speed of the electromagnetic waves, that will be equal to the speed of light, that is 3 into 10 to the power of 8 meter per second. So but as it was proved by Maxwell that electromagnetic radiation is a type of light. Okay, or you can say electromagnetic radiation is a form of light, but there is another debate after that whether light is a particle or wave. So before the development of quantum physics, it was considered that light is a particle. Okay, it was derived by Isaac Newton. So Newton thought that light was a particle because the edges of a shadow created was extremely sharp and clearer. Whatever the shadow we see, it is having some sharp and clear boundary. So because of this, the Isaac Newton considered that light is a particle. But there is a debate on the characteristics of the light. Okay, now second, another scientist, that is Christian Huygens, he considered that light is a wave. Okay, at the same time, Dutch physicist Huygens is a Dutch physicist. He believed that light was made of waves vibrating up and down perpendicular to the direction of light travels. So he considered that the light is a wave, whereas the Newton considered that light is a particle. So there was a debate of the characteristics of light, whether it is a particle or the wave. And also after that, Einstein first time he made some experiment to prove that light is a particle. Okay, so the theory of light, that is being a particle, completely vanished until the end of the 19th century when Albert Einstein revived it. Einstein believed that light is a particle that is made of very small teeny particles, very teeny component that is known as photon. Okay, but it is having dual nature. It is also considered as a wave. So that is a process of the dual characteristics of the light. That is a wave particle duality. So light is considered as a wave. Also, it is considered as a particle. There are a lot of experiments have been done to study the characteristics of the light by different scientists around the world. Okay, so there was a debate. This debate was until there was a discovery of photoelectric effect. Okay, so electromagnetic radiation has the properties of the waves as well as the properties of a particle. For an example, as we know that electromagnetic radiation is a kind of light. So when light behaves as a transverse wave nature, so we can consider light as a wave, but in the same at the same time, when we direct it at a substance, light can knock electrons off the substance. That is photoelectric effect. So this is the uh, experiment done by the Einstein to study the characteristics of the light. So this is the photoelectric effect. Photoelectric effect was very famous experiment. It was described by Einstein, and he got the Nobel Prize for this photoelectric effect. Because of the this experiment, photoelectric effect, it was believed that when we produce some light source, or you can say when the light interact with the metals, there may be the ejection of the particles. These particles will be in the form of different types of sources. Okay, so both the theories true in case of light. Light is having dual nature, and light is also a kind of energy. It's a form of energy. Sometimes it behaves like a particle, sometimes it behaves like a wave, and because of this, there may be the you can say the theory of the dual nature of the light. So the dual nature of the light is accepted, and current concept of the nature of the light, two experiments have been done, that is a particle and a wave characteristics. So the light source, when it passes through the barrier, so as it is made of small particles, so it produces the straight line that is a kind of shadow, and at the same time it is also having wave characteristics, so it can bend from when it passes through a barrier. If there is a barrier, so it bends into the shadow. So this experiment is very important, and these two experiments are very important to study the nature of the light. The dual nature of the light is accepted, and current concept of the nature of the light. Okay, so the dual nature of light states that light is having wave properties, that is having interference, diffraction, polarization. These three properties states that the interference, diffraction, and polarization is a kind of wave characteristics of the light, whereas the particle properties of light is based on the traveling in the straight line, the reflection and the refraction. So reflection and refraction, these two processes are very important in remote sensing, and also at the same time polarization is very useful for microwave remote sensing. So in remote sensing, we use the wave characteristics of the light as well as the particle characteristics of the light. Like when we talk about the microwave remote sensing, it is very much dependent on the polarization of the light, that is described on the basis of the wave property of the light. At the same time, when we talk about the optical remote sensing or reflected remote sensing process, that is based on the particle properties of the light. So dual nature of light is very important to study the electromagnetic radiation. Okay, so this produces a theory that is known as wave particle duality, and the light and other forms of the electromagnetic radiation behaves as a wave as well as a particle, and it was enriched or different scientists, de Broglie, Heisenberg, Schrodinger, these are different scientists. They made different experiments to study the wave particle duality of the light. Okay, so because of the wave particle duality characteristics of the light, we use different properties of the electromagnetic radiation in remote sensing process like polarization, reflection, and other processes are there. Okay, so as the photoelectric effect, this was an experiment done by the famous scientist Einstein. So after that experiment, after the photoelectric effect, after the experiment of photoelectric effect, the new branch of the physics comes into the light, that is a quantum physics. So most of the remote sensing processes is relying on the quantum physics, the quantum characteristics or quantum mechanics of the electromagnetic radiation. So before the development of quantum physics or quantum mechanics, Newton considered that what are different types of macroscopic phenomena such as motion of the billiard ball or rocket, whatever we see the motion means when there is a movement of the ball or any object, it's a microscopic phenomena, but that is failed to describe the microscopic phenomena. So classical mechanics and quantum mechanics, these are the two branches of the physics. Before the development of quantum mechanics or before the photoelectric effect, before the photoelectric experiment, it was considered that when there is a motion of an object, that is that can be explained on the basis of microscopic phenomena, and it was mostly studied by the Newton's mechanics and Maxwell's equation, that is based on the electromagnetic theory. But if we want to study the microscopic phenomena such as photon or atom scattering, because light is also having the particle nature, so there may be the particle that is known as photon. So if we want to study the microscopic phenomena, so we need to have different branch of the physics that is known as quantum mechanics or quantum physics. So quantum mechanics or quantum physics is a collection of different theories and different postulates that is based on the huge number of experiments by de Broglie, Heisenberg, and different scientists. So classical mechanics and quantum mechanics, these two branches are very important in physics, but the quantum physics is having more advanced mechanism to study the microscopic phenomena, means how different atoms and photons are interacting with each other and how they are responsible for the scattering mechanism, reflection, and other kind of processes that is useful in the remote sensing process. Okay, so the Heisenberg uncertainty principle is very important. It's a basic of quantum mechanics. So because the Heisenberg stated that we cannot specify the value of a particle's position and the momentum. Means there is uncertainty. We cannot measure the position and the momentum of any microscopic particle or any atom. So that is that is very famous principle that is known as Heisenberg's uncertainty principle, and the position and momentum of a particle is considered as the incompatible variables, and the Heisenberg uncertainty principle strikes at very first the heart of the classical physics. Okay, this concept Heisenberg uncertainty principle, first time they questioned the classical physics or classical mechanics. After that, people started thinking about the microscopic phenomena that is responsible, or that is the basis for the development of the quantum physics or the quantum mechanics. Okay, this is already discussed with all of you that photoelectric effect, it's also very basic experiment done in the quantum mechanics. So as we know that when the light it will be interacting with the object, the light can eject the electrons from a metal, but only if its frequency is above the threshold frequency. At a certain frequency, when the light interacts with the metals or any object, it ejects some kind of electrons. These electrons or these ejected particles are considered as a photon, or you can say these are the quanta. The name quantum physics comes from the term quanta. Quanta is a very small, very teeny particles, photons, that is ejected when a light interacts with any metal or any object. So classically, we cannot study the light as a wave, but because of the photoelectric effect, we can see or we can study the uh, you can say the particle nature of the light, and for that Einstein got the Nobel Prize in 1905. Okay, so these are some of the basics of quantum mechanics. Okay, so photoelectric effect provides some of the evidence that light is having particle nature. It also provides some evidence for the quantization process or the production of the quanta or photon. Okay, and when light interacts with the surface of a metal or any object, so there may be the possibility that some electrons may be ejected from that metal above the threshold value, and these electrons will only be ejected once the threshold frequency is reached. So this photoelectric effect is very important, and to understand how different frequencies or wavelengths are responsible for the ejection of the particles or different electrons from the metal or any object. Okay, so the electromagnetic radiation is generated when an electric charge is accelerated. Okay, there is electric field because of the movement, vibrating movement or vibration of the charged particles, negatively charged particles. And more generally, when we see the size and the direction of the electric and magnetic field is varied with the time at its source. Okay, so photoelectric effect is very important phenomena. It's very important theory to prove that the light is a particle as well as the wave. So the photon, or you can say these are the physical basis of the quantum physics. Photon is the physical form of the quantum physics. It's a basic particle, or you can say it's a important concept behind the study of the microscopic phenomena involved in the quantum physics. Okay, it deals with the physics of very small, that is particle, and their behavior at the atomic level. And the photon is also described as the messenger particle. Electromagnetic radiation, when the electromagnetic radiation travels through the space, so basically there is the propagation of the photon. These are the particles that describe the propagation of the electromagnetic radiation or electromagnetic wave as a smallest bundle of the light. So photon or quanta, it can also be known as the quanta or photon. These are the energy packets. These are very tiny particles. It holds the energy. So it is also considered as the energy packets. It was first identified by the Einstein in 1905 through the photoelectric effect. And these are the particles of the pure energy having zero mass at rest. Okay. And the demonstration of the quanta was based on the experiment done by the Max Planck in 1901. Okay, so these are the quantized light particle, light into packets called photon. It is having certain frequency, it is having certain wavelength. Frequency is denoted by the symbol nu, the wavelength is lambda, and its speed is always having the speed of light. So whatever the energy of the photon is equal to is calculated as the equation E is equal to h nu. E is equal to h nu is the energy of that photon or the quanta that was released by the metal or object. So higher frequency photons having high energy, that is having more damaging, and its momentum can be calculated using the equation h nu by c. Okay, where h is a Planck's constant. This is the constant. Its value is around 6.63 into 10 to the power of minus 34 joule second. Okay, so this is all about the photon. As we know that photon is a packet of energy that travels with the speed of light, and a photon of the red light has the least amount of energy in comparison to the shorter wavelengths. So when we talk about the visible portion of the electromagnetic radiation, so red portion of the light has the least amount of energy in comparison to the other part of the visible portion, or you can say the violet radiation or violet spectrum of the visible portion of the electromagnetic radiation is having higher tendency to release the energy with high intensity, while a photon of the violet light has the greatest amount of the energy. Okay, so there is a two term, that is polychromatic and monochromatic. Polychromatic is a kind of beam of the radiation, such as the form of sun, that is usually having a photon of the different energies. When photon travels at different energies, these kind of radiation or these kind of energy is known as polychromatic. And if the radiation or the energy source is traveling at a same kind of energy of the photon, that is known as monochromatic. Monochromatic means all the photons are having the same wavelength, or you can say it is having the same kind of energy, so energy level. And if the beam of the radiation is having different energy sources or different energy levels at different wavelength, it is known as polychromatic. Polychromatic and monochromatic electromagnetic radiation may be of two types, whether it is a polychromatic or monochromatic. And the distribution of all the photon energies over the range of the observed frequencies embodied in the term of spectrum. So depending on the wavelength, we may have different types of the photons. If we are having wavelength at different wavelengths are there, if wavelength is different, then we may have different energy sources. Then different energy sources means we are having the photons with different energy levels. And if the radiation or electromagnetic radiation is traveling at the same wavelength, it is considered as a monochromatic source of the radiation. Okay, the black body radiation is very important. It is also the basis for the quantum mechanics. It is known as that when a material is heated, it radiates the heat, and the amount of the heat, or you can say the radiation that is releasing or radiating from that object or material, depending on its temperature. Okay, for an example, when we are having the bright red, or having orange, yellow, and finally the white red, the emission spectrum depends on the material. Whatever the material is there, different materials may have different types of particles, different types of energy levels in the atoms of that molecule. Okay, so black body radiation depends on the material, and depending on the material, we may have different emission spectrum. Okay, and it was described by Max Planck, and he also got the Nobel Prize in 1918 for the black body radiation principle. Okay, the Planck he gave an equation, that is Planck's equation, is equal to h nu is equal to total amount of energy that describes a photon or quanta that is traveling with the speed of light, where h is the Planck's constant, and a photon or quanta is said to be quantized for any given poses a certain quantity of the energy. So when we want to measure the energy of any photon or quanta, we should know the frequency, or you can say the wavelength of that photon or energy, so that we can easily calculate the amount of energy of that photon or the particle. Okay, so this is the way how we can calculate the frequency and the speed of that radiation, or the, you can say, the photon. Okay, c is equal to lambda nu, or nu is the frequency, is equal to c by lambda. And when we replace the value of c mu in the equation e is equal to h nu, we will get the equation, that is e is equal to hc by lambda. So this is the Planck equation. You see the energy E is inversely proportional to the wavelength. Means higher wavelength will have low energy, low wavelength will have high energy. E is equal to hc by lambda, where energy is inversely proportional to the wavelength of the light, or you can say the wavelength of the radiation. Okay, this is another Planck equation, that is Planck equation. Okay, so as we know that the photons or the quantas, different, these are the energy packets, and they travel with the speed, they travel at the higher frequencies. therefore they are having more energy. But if a material under excitation experience a change in the energy level, sometimes what happens, the charged particles or the quanta or photons in the metal, they get excited after having the external energy source. So they reaches to the higher energy level from the lower energy level. So when they go from lower energy level to higher energy level, they remain at that position at certain time. But when they again started moving towards the lower energy state, they release amount of energy in terms of photon or in terms of energy, that is a kind of radiation. Delta E is equal to E2 minus E1, means the difference of the energy level of the quanta when it is moving from lower energy state to higher energy state. Because of this movement, they release amount of energy in terms of quanta or photon, that is having energy that is equal to h nu. Okay, so black body is a kind of material that absorbs all kind of radiation. Okay, but it is not possible to have the black body in the nature. It's a hypothetical concept of having a material that absorbs all type of radiation. Okay, so a black body is a kind of perfect absorber. It is considered as a perfect absorber, means the black body absorbs all kind of radiation that is reaching to that body or that object. Okay, but it is a hypothetical concept. No body or no any such kind of black body exists in the nature that absorbs all kind of radiation, all type of energy sources. Okay, these are the fundamental radiation laws. Planck's law, it is already discussed with you. Black body law, Wien's displacement law, Stephen Boltzmann law. Okay, so black body is a hypothetical body. It completely absorbs all the radiation. Okay, and the black body radiation is explained by Planck. They explained the distribution of the spectral response and energy level of the radiation that is emitted by the black body. This is the equation which is written here. It is used to calculate the energy that is emitting at a certain wavelength, E lambda. Lambda is a certain wavelength. At that certain wavelength, the amount of energy that is releasing by or that is radiating by that object is equal to 8 pi h c upon lambda to the power 5 is equal to 1 upon exponential of hc upon k t lambda minus 1. So this is the equation. Through using this equation, we can easily calculate the amount of the radiation or the energy that is the amount of energy that is radiating by that object at a certain wavelength. Okay, Wien's displacement law, it is very important in remote sensing that it calculates the relationship Kelvin. Okay, it means when we want to see the relationship between the amount of energy releasing by a black body at a certain wavelength, it may be the directly relation with the temperature. Lambda max is equal to k by t. T is the temperature. Okay, so the wavelength at a the maximum wavelength will be will be achieved at a certain temperature of that body, and where k is the constant that is having the value 2898 micrometer. Okay, so Wien's displacement law is very important in thermal remote sensing process. It helps us to see the relationship between the temperature of the body as well as the amount of energy that is radiating from that object at a certain wavelength. That will be considered as a dominant wavelength lambda max. The amount of the energy, or you can say the amount of the radiation coming after the object get heated, having some temperature, it is having the maximum wavelength lambda max at a temperature up to a certain range. That is Wien's displacement law. It is having different range. You see at different temperature we may have different wavelengths. We may have the radiation with different wavelengths. Okay, Stephen Boltzmann law is a very important mechanism. It's a very important rule that gives us the information about the energy of a black body. and its equation is very simple. E is equal to epsilon. This is the term epsilon t to the power 4. Means the amount of energy is directly inversely, or you can say directly relation with the temperature. The object having higher temperature will be the tendency to release the higher amount of the energy, and it is having the force power of the temperature. E is equal to sigma t to the power 4, where sigma is the constant, and this equation calculates the amount of energy that is emitting by an object, and it is a function of temperature. If object is having high temperature, it will release high amount of energy. If the object is having low temperature, it will have low amount of the energy. Okay. The thermal properties of the black bodies, as we know that black body is hypothetical object. If it is a hypothetical object, it is considered that it absorbs all type of radiation, but it is not possible, so that it may have some kind of reflectivity and transmission process. Okay, so ideally it should have the value of 1, but in reality, or in the real world, it is having reflection as well as the absorption process. Okay, so the thermal properties of the earth material can be described, can be studied with the help of the black body radiation principle. But the black body radiation principle tells us that there will be the completely absorption of the radiation, but still in the real world, there is no such object that completely absorbs all kind of radiation. There may be very slight reflection as well as the transmission. There is no complete absorption of the radiation on the that is striking on the object. Okay, heat transfer. So there is a process of conduction when there is a molecular contact. If the objects or the molecules of two different objects are having with the contact with each other, there may be the conduction. Through the conduction process, there may be the transfer of the heat from one object to another object. Convection is another process through which we study the molecular movement or the circulation of the molecules within the object. So conduction means when we physically contact two objects at different temperature, so there may be the conduction process through which the heat or the energy or the temperature will be transferred from one object to another object. That will be the process of the conduction. Whereas if there is a molecular movement within the object, within the same object, that will be the responsible for the heating of an object. That is a molecular movement or the circular movement of the molecules within the object. And the radiation is the amount of electromagnetic radiation after reaching at a certain level, after reaching at a certain temperature. Most of the earth surface features radiate energy. That will be in terms of thermal infrared radiation. Okay, these are the infrared spectral bands used for remote sensing process. Reflected portion of the electromagnetic spectrum, that is ranging from zero point 0.7 to 3 micrometer. It comprises blue, green, and red spectrum. Then there may be the thermal process, thermal bands that will be a kind of wavelength interval between 3 to 14 micrometer, and it is having a these are the kind of you can say the energy that is left after the absorption by the atmospheric gases and particles. And the radiant energy peak is a kind of radiant flux, that is a total amount of energy. Radiant flux is the total amount of energy that is either radiated or reflected or emitted from the object at a particular wavelength. Okay, that is studied, that is described by Wien's displacement law. Okay, radiant flux is the kind of, you can say, the total amount of radiation that is outgoing, and it can be studied, it can be described through the process of the through the law of Stephen Boltzmann. Okay. Sorry for the interruption. There was a power cut. I think my slides are visible to all of you.
Yes, sir.
Yeah, there was interruption because of the electricity cut. Power supply
Yes,
was
sir.
not here. Okay, so I was discussing about the radiant flux. So it's a kind of, you can say, the total amount of the radiation, or you can say the amount of radiation, whether it is outgoing radiation, or you can say the emitted radiation, absorbed radiation, or you can say the reflected radiation. That is known as radiant flux. Okay, emissivity is a kind of amount of radiation. All the natural objects, they emit a fraction of their maximum possible black body radiation. So emissivity of different objects depends on the molecular composition or the structure of that object. Emissivity is the ratio between the actual radiance that is emitted by a real world object and a black body at the same thermodynamic temperature. Its equation is written here. Mr by Mb means the actual radiance that is emitted by a real world object and the amount of radiation emitted at a particular temperature at a particular wavelength. So if the emissivity of an object varies with the wavelength, the object is said to be the selective radiant. Okay, so this is the way how we can study the interaction of electromagnetic energy at atomic level. Okay, Niels Bohr was a scientist. He described the interaction of electron, or you can say the interaction of electromagnetic energy with the electrons, charged particles in the nucleus, in the molecule or atom of that object. Okay, so when we supply external energy E is equal to h nu to the electrons that is revolving around the nucleus of an atom. Okay, and when it get heated by the external energy source, the electrons which was in the lower energy state will be reached to the higher energy state, or you can say the excited energy state. Okay, it remains at the excited energy state at a certain time, and again it reaches back to the lower energy state. During this process, it emits a certain amount of energy that is a kind of, you can say, the in terms of photons or quanta. Okay, so it is described by the this kind of movement of the electrons or charged particles around the nucleus of an atom was described by Niels Bohr. And this process, whatever I have shown here, this is a kind of way how we can see that when we supply the external energy source to the atom, the electrons will be moved from lower energy state to higher energy state, and it will reach a certain amount of energy, then it again going back to the lower energy state. Okay, this was the first time this such kind of experiment was done, and this is the basis for the process of the atomic interaction of the particles at atomic level. Okay, it was first done for the hydrogen atom, where uh, the external energy source, or you can say the amount of energy, when we supply amount of external energy source to the atom, okay, they release a certain amount of energy that is having different wavelengths. Okay, it is described by the Lemon series, Balmer series, and the Paschen series. So the hydrogen atom releases certain amount of radiation in different wavelength intervals. It will be released in the infrared radiation, that is Paschen series. Then visible portion is also released by the hydrogen atom, that is a Balmer series, and it also radiates or emits certain amount of the radiation, that is the ultraviolet radiation or the Lemon series. Okay, so this is the way how we can describe the process of the emission of different radiation by an object. Okay, in the nucleus, we know that in the nucleus we are having protons and neutrons, and electron revolves around the nucleus, and after supplying the certain energy to the electrons revolving around the nucleus, it will it get excited and reach to the higher energy state. And when again it going back to the lower energy state, it releases a certain amount of radiation, certain amount of energy at different wavelength interval. It may have visible portion, it may have thermal infrared portion, all the ultraviolet portion. Okay. So the interaction of electromagnetic energy may be at two different levels, that is having microscopic level and the megoscopic level. So it is already discussed, or you must know that the process of the atmospheric absorption, different atmospheric gases, oxygen, carbon dioxide, ozone, they are a kind of you can say they are responsible for the atmospheric absorption of the radiation. Okay, at different altitude above the sea level, we may have different composition of the atmospheric gases. Ozone gas is there, carbon dioxide is there, different water molecules, water droplets are there, aerosol particles are there. So depending on the composition of the gases in the atmosphere, there may be different you can say there may be the different absorption process of the radiation that is coming from the sun. Okay, so you see this is the way how we can see or how we can study the absorption process at different levels of the atmosphere: troposphere, stratosphere, mesosphere, then thermosphere is there. So at different layers of the atmosphere, we may have different types of gases, we may have different atmospheric gases and particles, and depending on the radiation coming from the sun, there may be different absorption process in the upper atmosphere. Okay, this is the interaction of electromagnetic energy when it reaches to the surface, that is studied at a megascopic level. Okay, there may be the process of the transmission, reflection, and the scattering. Some part of the energy can also be absorbed by the earth surface feature, that will be released in the form of thermal energy or thermal uh, radiation, that is also known as emitted energy. Okay, so whatever the energy reaching to the earth surface after the interaction with the atmosphere, it may be transmitted by the object, it may be reflected, or there may be the process of the scattering on the earth surface, or there may be the absorption process, and the energy which is absorbed by the earth surface will be emitted after some time by the object in the form of thermal energy. That is the basis for the thermal remote sensing process. Atmospheric scattering is also there. It is already discussed with all of you that different gases, different dust particles, different types of water vapor is there in the atmosphere, and the solar radiation is having a kind of particles that we call it as a photons, or you can say the quanta. They interact with the atmospheric gases, they interact with the water droplets, they interact with the smoke and dust particles, and because of that there may be the process of Rayleigh scattering, Mie scattering, and the non-selective scattering. Okay, this is the way how we see that atmospheric absorption occurs in the upper atmosphere. Okay, and this is the atmospheric window. Atmospheric windows are a kind of certain wavelength intervals for which atmosphere behaves as a transparent medium.
वरुण,
Yes.
मैं बोल रही हूँ थक जाओगे तो 2 मिनट ब्रेक दे देना बच्चों को भी और खुद भी.
Yes, just after 5 minutes I am having second lecture, मैम. इसके बाद तो अभी इसको
हाँ,
खत्म करके then 5 मिनट के लिए ब्रेक करेंगे.
हाँ.
Okay, so this is the atmospheric window. The concept of atmospheric window is a kind of process through which we can see that the amount of the wavelength interval or different wavelength intervals that can pass through the atmosphere, or you can say the wavelength intervals for which atmosphere behaves as a transparent medium, through which these wavelength intervals, these radiation can easily pass through the atmosphere and can reach to the earth surface. This is known as atmospheric windows. Okay, terrain energy interaction. So after reaching the radiation to the earth surface, there may be the interaction with the terrain and the matter. Okay, the rate of the flow of energy through a surface is called radiant flux. Radiant flux is the total amount of the energy that is flowing towards the Earth's surface. Okay, that is known as radiant flux. It is measured in the watts. Okay, and this is the equation that tells us the total radiant flux is equal to the amount of energy that is reflected, absorbed, and transmitted at a certain wavelength. Okay, this is the simplest equation of the terrain energy matter interaction, that is known as radiation budget equation. The total amount of radiation that is coming from the sun will be equal to the total amount of reflected energy, total amount of absorbed energy, and total amount of transmitted energy. But this is the ideal condition. It is not possible every time to get the exact the total amount of incoming radiation and the total amount of the outgoing radiation. This is the process. Irradiance is the total amount of incoming radiation that is reaching to the Earth's surface, and the exitance is the total amount of radiation, that is radiant flux, at a certain wavelength, that is leaving the Earth's surface at a particular wavelength. Okay, so radiant flux density can be studied on the basis of irradiance and exitance. Radiance is a kind of, you can say, total amount of radiant flux that is leaving the Earth's surface at a particular angle from a unit area on the Earth's surface. Okay, so this is the way how it leaves the Earth's surface, the amount of energy that is leaving the Earth's surface. Okay, these are some of the equations that is used to calculate the amount of radiation leaving the Earth's surface, that is radiance. Irradiance is the amount of energy that is reaching to the Earth's surface from all the direction. And exitance, the reflectance factor, that is also very important, how much energy can be reflected by the Earth's surface at a certain angle. And irradiance, exitance, and reflectance, these three quantities, these three terms are very important for the remote sensing process. Okay, and the amount of energy which is absorbed in the upper atmosphere and the lower atmosphere means whatever the energy is reaching to the Earth's surface. So we can calculate the bottom of atmospheric reflectance, and whatever energy we consider at the top of the atmosphere is considered as the top of atmospheric radiance. So TOA and BOA, these two terms are very important. These are kind of energy, or the kind of electromagnetic, the type of energy, radiation, the amount of radiation that is calculated at the top of the atmosphere as well as the bottom of the atmosphere. Depending on the requirement, we can calculate the top of atmospheric reflectance, that is TOA, and the bottom of atmospheric reflectance, that is BOA. This is a kind of actual reflectance from the Earth's surface, actual reflectance from different land surface features. Okay, these are the equations. These are kind of, you can say, the terminologies that is used to describe the radiance, and you can say the top of atmospheric radiance and bottom of atmospheric radiance. Okay, this is another example how the signal that is calculated by this received by the sensor, that is top of atmospheric radiance, and when we calculate the radiance on the bottom of the atmosphere, that is known as bottom of atmospheric radiance. Okay, so now here I am going to take a break for 5 minutes, then I will start another important topic, that is active remote sensing, and we see different physical basis behind the active remote sensing process. So till now we have discussed about the different physical bases of passive remote sensing, including the reflected infrared radiation or thermal infrared remote sensing process. So here, if you have any question till now, then you can ask. Then we will start another part of today's lecture that comprises the active remote sensing process.
Thank you, sir. It was very nice lecture about remote sensing, physics of remote sensing. Sir, please share these slides also, because these are very good slides, so we can also
Yeah, sure. I will share with all of you. So if you have any doubt or questions related to the physical terminologies that is used in the remote sensing process, you can ask anything. So for that, actually, the physics of remote sensing is, you can say, electrodynamics is a branch of physics that is very useful when we want to study or when we want to describe different physical processes used in the remote sensing process. Okay. So electrodynamics, or you can say the quantum physics, is very important. Quantum physics is very important to describe different phenomena used in the remote sensing process.
Yes, sir, you covered from basic to the quantum mechanics, all things. So it is
Yeah,
very nice.
yeah. These are some of the basics, but it's a very lengthy topic, so it is not possible to cover each and everything. But these are some of the overviews. Means I have shown you the basic terms, overview of basic optics, or you can say the quantum mechanics terms in the remote sensing.
Yes, sir. Thank you,
Okay.
sir.
So almost 10 to 20 slides are left that will be related to the active remote sensing. I will cover it after just after 1 or 2 minutes. Okay. So now I'm going to start the remaining part of the today's lecture, that is having some basic concepts of active remote sensing. Till now, whatever we have discussed, that is for the optical remote sensing process, that you can call it as a reflective remote sensing or emitted remote sensing. Now we are going to see what is the active remote sensing process and what are the basis for the active remote sensing. So this is another important type of remote sensing process in which we use the active sensors, or you can say the artificial source of energy. In the optical remote sensing or the thermal remote sensing, we use a natural source of energy, that is a kind of electromagnetic radiation. But sometimes when we want to collect the data sets in the night time, so we need to provide own source of energy, that is known as active microwave, or you can say the active remote sensing process. And lidar is also a kind of active remote sensing process in which we use the shorter wavelengths of the electromagnetic radiation as a light, as a laser light, to record some of the backscattered energy from the terrain or from the target, from the atmospheric particles. Okay. So space-borne imaging radar, whatever the active remote sensing or active sensors we use for remote sensing process, it is also known as space-borne imaging radars. Imaging radars are a kind of radar system that is used to acquire the images about the ground surface, that is based on the transmitted pulse or the returned signal after the interaction with the Earth surface features. Okay. So this is the way how this active microwave or active remote sensing process works, where we produce or we send our own energy source towards the target on the Earth surface, and these energy sources will be transmitted in terms of pulses. Okay, and these pulses interacts with the object on the Earth surface and return back and received by the sensor. Okay, so it can be done, means active remote sensing can be done using the radar component. Radar is a kind of instrument, it's a kind of system that consists a transmitter. That transmitter is used to transmit the pulses or energy source towards the target. A receiver receives the energy that is coming from the target on the Earth surface by some antenna is used to conserve the out incoming, or you can say the energy coming from the target after the interaction. And there may be a electronic system that is used to process and record the data. Okay, so this is the way how it works. Means there is a transmitter. It's a very small animation. There is a transmitter. That transmitter is used to transmit the signals. Basically, these signals are the microwave signals. These are the longer wavelengths of the electromagnetic radiation. Duplexer is a term. Duplexer is an instrument that is used to behave two times, or you can say it is having dual nature. Means at a time when it transmits the signal, it allows only the transmitted signal, and when it is receiving the backscattered signal, it behaves as a receiver. So duplexer works two times, as a transmitter as well as a receiver, and the energy coming from the target after the interaction with the target on the earth surface will be received by the sensor. Okay, so this is the principle of the SAR, or synthetic aperture radar. So what happens? The radar uses an electromagnetic carrier as a frequency, or you can say these are the microwave signals of the electromagnetic radiation, and the radar generates a pulse, and each pulse is transmitted towards the target, and it propagates with the speed of light, and the fraction of the incident energy that is reflected back towards the radar is gathered by the receiving antenna. Okay, so this is the way how these radar pulses will be sent towards the target from the aircraft. Okay, so you see the direction of the arrow, the direction which is towards the target is the transmitted pulses, and when it interacts with the target on the earth surface, the return pulses having lower intensity in comparison to the incoming energy or incoming signal. The incoming signal or the pulses which was transmitted towards the target having high intensity level, high energy level, but when it interacts with the target on the earth surface, there may be some kind of loss of the energy, there may be the scattering process, there may be some kind of absorption and other processes. So because of this, the return signal or the return pulse will be having low intensity, low energy level in comparison to the incoming radiation or incoming signal. Okay, this is the concept of the synthetic aperture radar. Radar was a system, but the radar system having some antenna. That antenna is used to conserve the energy or the signal coming from the target after the interaction. But it is not possible to carry a larger antenna with the system in the space. So there is a term comes into the scenario, that is synthetic aperture radar. So the synthetic aperture radar means we synthesize the use of the antenna. We synthesize the antenna size, means whatever the information is collected by the sensor at a first observation, and the last time the sensor observes the object. So this forward motion of the SAR system from the first observation to the last observation, the distance traveled through this process from the first observation to the last observation, the total amount of the incoming signal received by the sensor will be considered as a larger antenna. That's what is known as synthetic aperture. Synthetic aperture means it's a kind of, you can say, the synthetic aperture. Aperture means the antenna, and it is actually not a antenna, but it is synthesized to work as a larger antenna, so that we can conserve the most of the incoming signal coming from the target on the earth surface after the interaction of the microwave signal during the first observation and the last observation. Okay, so now moving to the next slide. These are some of the microwave bands. The microwave signals are having different bands. Depending on the requirement, we use different microwave bands for different applications. There are different number of bands used in the microwave remote sensing or active remote sensing, that is having Ku band, X band, C band, L band, P band. Okay, so different bands may have different, you can say, different applications, and different countries have launched their sensors, satellites at different wavelengths, or you can say different microwave bands. They work at different microwave bands, starting from the X band, C band, and the S band. Okay, these are some of the characteristics of the radar system. They uses the electromagnetic waves having different frequencies. Frequencies are measured in terms of gigahertz and megahertz. Okay, and most of the time we measure the frequency of the electromagnetic waves in gigahertz. Okay, and it is governed by the Maxwell equation. And as we know that microwave signals are a kind of electromagnetic radiation, and it travels with the speed of light. And whatever the antenna is used in the radar system, it is used to receive the incoming radiation or incoming microwave signal after the interaction with the earth surface feature. Okay, so active sensors provides its own source of energy. They illuminate the target, they artificially illuminate the target on the earth surface, and for that they use the transmitter and the receiver. Transmitter transmits the energy to illuminate the target on the earth surface, whereas the receiver receives the incoming radiation coming from the object after the interaction. Okay, so these are some of the terminologies and technologies used in the radar. Radar are the systems that involves a wide range of technologies, and it is a kind of new and emerging technologies that is based on the capabilities of the microwave signals, based on the capabilities of the microwave pulses that can be used to detect and identify different land surface features. Okay, so in radar we use some antenna. Antenna is very important. It's a kind of instrument that is having multiple roles. It is used for the impedance transformation, that is a kind of free space intrinsic impedance to the transmission line characteristics, and it is also used for the propagation mode adapter, and sometimes it is used as a spatial filter that is useful for discriminating the radiation pattern coming from the target. Means whatever the energy that is coming from the earth surface feature after interaction with target. So spatial filters can be used to distinguish different radiation pattern, or you can say the direction dependent sensitivity. Polarization is very important. Calibration is already discussed with all of you. Calibration is very important. Whatever the signal is received by the sensor, it should have some calibration. Okay, so these are another kind of terminologies. Scattering is very important. Whatever the signal is reaching to the earth surface, it will be scattered from the object depending on the shape and composition and orientation of the object. Different objects may have different composition, different orientation. So depending on the object type, there may be different types of scattering mechanism. Either it may be specular reflection, or it may be Kirchhoff scattering, Bragg's resonance. These are kind of scattering mechanism that can happen on the earth surface when the microwave signal interacts with the object. Okay, there may be the volume scattering. Volume scattering is of two types. It may have Rayleigh scattering and Mie scattering, and different materials may have different permeability and permittivity processes, though that is used to see the process of the absorption. Means different materials may have different conductivity. They have different dielectric properties. Depending on their materials, depending on their properties and characteristics, we may have different absorption levels. Okay, so microwaves are having oscillators. These oscillators are kind of uh, instrument or part of microwave or radar system that is used for phase locked loops. Means whatever the signal it generates and transmitted towards the target, it will be in the phase locked loop, and that is having certain frequency that is synthesized, and it may have different filters. These filters can be used to discriminate different types of radiation coming from the target. Okay, so digital, the whatever the signal that is received by the receiver in the radar system, it may have digital mechanism. Means it can record the timing of the incoming signal. Whatever the pulse that is received by the receiver, it is having certain frequency, so it also measures the pulse repetition frequency. That can be very much useful for the showing the incoming radiation or microwave signal after the interaction with the target. Okay, there may be different types of system geometry, monostatic, bistatic. Monostatic means if we use two, you can say if we use transmitter and receiver separately, that is monostatic system. In the bistatic system, we use the same instrument as a transmitter and the receiver. Okay, so there may be the two types of radar system, monostatic and the bistatic. In most of the cases in spaceborne remote sensing technology, we are using monostatic radar system. That is a kind of, you can say, the transmitter and receiver both are two different components. But in the bistatic, we use the same setup as the transmitter and the receiver. Okay, signal processing can be done by different Fourier analysis. Then we can also have different filters. We can apply different low pass and high pass filters for getting the information about the incoming signal coming from the target after the interaction with the earth surface features and the object on the earth. Okay, so penetration ability to the forest, microwave signals or the microwave bands are having different penetration abilities. If we want to study the forest, okay, X band, C band, L band are the commonly used microwave bands that can be used to study the forest type, forest canopy, because these three bands are having different penetration capabilities. L band having different penetration capabilities, it is having more penetration capability in comparison to C band and X band. X band is having less penetration capability. So if you want to study the underground objects beneath the forest cover or forest canopy, then it is very useful to study the L band microwave signal that can easily penetrate through the forest canopy and can reach and can interact with the target beneath the forest cover. Okay, there may be different types of scattering process. It may be surface scattering. If there is a scattering from the top of the canopy, from the leaves of the forest tree, that is a surface scattering. If it can penetrate through the forest canopy and can interact with the branches and other part of the trees of the forest, it may have volume scattering. And when it reach to the ground, and so there may be the two types of scattering, whether it is a surface scattering and the volume scattering, and in some cases it may have both the scattering, that is surface scattering and the volume scattering. Okay, so radar imaging geometry, this is the radar imaging geometry. It may have some flight direction that is described by the symbol A with the nadir point. Nadir is the position of the sensor at the perpendicular position from the position of the sensor below above the ground. Then there may be the swath that is described by the C, which is the area that is illuminated on the target on the earth surface, and the range D refers to the cross track dimension that is perpendicular to the flight direction. Okay, this is the direction that is perpendicular to the flight direction A, and azimuth refers to the along track dimension that is parallel to the flight direction. So the sensor, or you can say the radar sensor, captures the information in the range direction and the azimuth direction. The range direction is the direction perpendicular to the flight direction, and the azimuth direction is the direction parallel to the flight direction. Okay, depression angle and incidence angle. Okay, depression angle is a kind of, you can say, the angle between the horizontal plane extending out from the sensor and the electromagnetic pulse of the energy from the antenna to the specific point on the ground. Whereas the incidence angle is the angle that is used to measure the angle between the perpendicular line toward on the earth surface and the signal that is coming from the sensor and interacting with the object. Okay, this is a near and far range, the portion of the image swath closest to the nadir track. If the position is near to the nadir, that is known as near range, and if the position is far from the nadir, that is known as far range. Incidence angle, this is the A is the incidence angle, which is the angle between the radar beam and the ground surface, perpendicular line to the ground surface, which that increases with the moving across the swath from near to far range. Look angle is the angle, that is the angle through which the radar looks at the surface. Slant range, okay. Slant range is the kind of radial line of sight, distance between the radar and each target on the surface. Ground range distance is the true horizontal distance along the ground corresponding to each point measured in the slant range. These are some of the terminologies in the radar geometry. These are very important to know how different terminologies are used in radar geometry, and this is very much useful for getting the information. The polarization is also very important. It is a characteristics of the electromagnetic radiation. As we know that electromagnetic radiation travels in both directions, either vertical or horizontal motion. Okay, so polarization refers to the electric field direction of the electromagnetic radiation, and most of the radar systems are designed to transmit microwave radiation either horizontally or vertically. So this is the way how we can describe the polarization. Initially, if the light is unpolarized, so it travels in all the directions. But when we allow the light to only travel in the certain direction, either vertical or horizontal, it is known as polarized light. So polarization can be done with the help of some polarizer. It's a kind of system that only allows the light to travel in either horizontal direction or vertical direction. Okay, this is the concept of the polarization. Polarization is very important in microwave remote sensing. Whatever the signal we transmit from the radar system, whether it will be vertical direction or horizontal direction, and depending on its interaction with the target on the earth surface, we receive the vertical and horizontal direction of the signal. So VV means vertical transmit, vertical receive. HH means horizontal transmit and horizontal receive, and HV and VH are the cross polarized, means we transmit the signal in the vertical direction and we receive the signal in the horizontal direction. So this is the way how you can see the difference between vertically polarized light and horizontally polarized light. Vertically polarized light and horizontally polarized lights are used for different applications. If we allow only vertical direction of the signal, it is vertically polarized light. If we allow only the horizontal direction of the light, it is known as horizontally polarized light. So whatever the signal received by the receiver depends on the composition of the material, orientation of the material on the earth surface. The polarization HH, there may be the four types of polarization: HH, HV, VV, and VH. HH means horizontal transmit, horizontal receive. In the same way, HV means horizontal transmit and vertical receive. So this is the way how we can use different polarization images with the visible light. Means the same study area can be visualized in two different ways when we use vertical polarization light and horizontal polarization light. This is the radar equation. This is the bistatic radar system in which you see there is a transmitter that transmits the signal, and there is a receiver that receives the signal after the interaction with the target, after the interaction with the object. So there are different terminologies: gain pattern of the antenna, then what is the spreading loss, some part of the energy can be lost after the interaction, then after the spreading loss, very small amount of the energy will reach to the target and it interacts with the target and received by the receiver. So how much energy is received by the receiver is dependent on the effective area, means how much area is get interacted with the target signal coming from the transmitter. Okay, this is another example. This is the equation that will be used to study, that will be used to calculate the radar range equation, or for in case of monostatic area. Thank you very much for your patience listening of the lecture. If anyone have any question, then you can ask. Hello, am I audible?
Yes, sir. Your lecture was very detailed and informative, sir. And so many things I brush up because I did my PhD diploma in remote sensing.
Okay.
So I really brush up all things. and several things I got from your lecture. Thank you, sir.
Okay, thank you very much. If anyone have any question, then you can ask, and I will share this PPT with all of you, so you can go through these terms. And for more detailed study of these terms, so you should go through some books on the quantum mechanics. Okay, so thank you very much for listening this lecture.
Thank you, sir. Any questions?
Okay, sir. So
Okay, then on the behalf of Center for Climate Change and Water Research, I again thank Dr. Varun Narayan Mishra because he's a core team member, so I'll not be appraising a lot of words, but still, he has given us in detail information about physics of remote sensing because he's a physicist by uh, background. That's why he was able to justify the topic with a more in detail finding related to the topic. Generally, whenever you are reading anywhere in India, when you read about remote sensing and GIS, basically the persons who are pursuing remote sensing and GIS are from majority from geographer or environmentalist. But if you see that the basic principles of remote sensing is based on physics, so he is one of the rare person with a physics background and thereafter a specialization in remote sensing and GIS. So that's why the kind of information that he has given us today, I doubt that till date you have never find in India and will never find anywhere else in India in coming days. So thanks, Dr. Varun, for making all
Hello.
this
thank you very
very
much,
Hello,
sir.
sir.
informative. Yeah,
Sir,
yeah,
sir,
yeah.
I have a question, sir. Sorry for the delay. Sir,
Yes,
sir, I'm a
मेरे से
little
कि
bit
वरुण से
confused about
मेरे से किससे
emissivity and radiance.
मेरे
yes,
से है कि वरुण से
Varun, sir.
ठीक
yeah. Emissivity and radiance.
Radiance. Yes, sir.
Okay, so when we talk about the emissivity, so emissivity depends on the amount of radiation that is absorbed by that material. Okay, how much it will absorb, that then it will emit some kind of energy. Radiance is the amount of energy that is reflected by the object without any kind of absorption. That is the radiance. Okay, I got you got the
Yes,
point.
sir. Yes, sir. Yes, sir. Yes, sir. Thank you, sir.
Emissivity
Thank you
means
very much.
first it absorb, then it emit, and radiance is directly it is reflected from the target of the surface.
देखो हुआ है कि नहीं
Yes, sir. Very clear, sir. Thank you, sir.
Sir, I
Okay,
have a
thank you.
question.
अजय कहाँ है
Yes,
Sir, can we use a single platform for both passive and active remote
मेरा
sensing?
ले लो तुम अपना ले लो
we can use because since on a single platform we can use multiple sensors, so we can use two different types of sensors on a single platform. It can be done, but for that you need to define the path and the timing of the image acquisition. Generally we use the optical sensors of different types on the same platform, but you can use optical as well as the microwave sensors on the same platform to get the image. No issues, we can do it.
Okay, sir. Thank you, sir.
Sir, I have a question, sir.
Yes,
Sir, what is black body in remote sensing, sir?
a black body is you can say black body is a kind of object that absorbs all type of radiation. So remote sensing is based on the reflectance and transmission and absorption. So black body is a hypothetical body. It is not possible to have the black body in the real world. तो ब्लैक बॉडी अगर है अगर वहां पे, तो ब्लैक बॉडी की बात करते हैं, तो ब्लैक बॉडी मतलब कि कोई ऐसा ऑब्जेक्ट अर्थ पे है जो कि सभी जितना भी रेडिएशन आ रहा है अर्थ से सन से उसको पूरा एब्जॉर्ब कर लेता है, बट ऐसा होता नहीं है एक्चुअली. सो ब्लैक बॉडी इज नॉट पॉसिबल इन द रियल वर्ल्ड. लेकिन हाँ, अगर ब्लैक बॉडी अगर होता तो फिर रिमोट सेंसिंग के रिस्पेक्ट में फिर सेंसर हमारा क्या है, सेंसर को कुछ इंफॉर्मेशन नहीं मिलता, क्योंकि पूरा तो पूरा वो एब्जॉर्ब कर लेता वो ब्लैक बॉडी. वो ना कुछ रिफ्लेक्ट करता ना कुछ उसको आगे ट्रांसमिट करता. सो
Yes.
ब्लैक बॉडी एक हाइपोथेटिकल टर्म दिया गया है कि अगर जितना भी सोलर रेडिएशन आ रहा है उसको एब्जॉर्ब कर लिया जाए तो दैट इज अ ब्लैक बॉडी. But in that case, remote sensing sensors will not be able to receive any kind of reflected energy, क्योंकि सब तो एब्जॉर्ब हो जाएगा, वो तो कुछ रिफ्लेक्ट करेगा नहीं.
Okay, sir. Thank you, sir.
Sir, I have a question also.
Yes.
Sir, black body and black hole are the same concept or different?
No, that is different thing. Black body and black hole are different things. Black hole means it is not specific to a particular wavelength. It absorbs all the radiation, and black hole is a kind of object that is having a large mass, large volume. But whereas in case of black body may have very small mass, very small volume. So black body is another term, and black hole is a kind of large mass volume that can be used to even they can absorb the light, cannot pass through the black hole. And black body is a very small amount of small body, small mass. Okay.
Okay. Thank you, sir.
Okay. Anyone have any question?
Hello. Yes, sir. Any questions? If not, we'll move on to our next session. Within few minutes, our next speaker will join. We are just waiting for him to join. As I have called him, he said within 2 minutes he will be joining us. So within 2 minutes, we'll start our next program. Upasna,
Sir.
you may start the next session.
Moving ahead, I'd like to introduce to our next speaker, Dr. Ajay Kumar Talur sir. Dr. Ajay Kumar Talur sir is working as an assistant professor in Department of Remote Sensing and GIS in the University of Jammu. Dr. Ajay Kumar Talur sir has obtained his doctorate in remote sensing and GIS application in hydrogeology from University of Jammu. 13 years of research experience in the application in geospatial technology for natural resource management for land and water resources. He has excelled twice with Best Paper Presentation Award in India, being an expert of remote sensing and GIS application in water sciences, cryosphere and climate change, tectonic and quaternary geomorphology. He is working on two major research projects on using space-based inputs for glacier mapping and climate change in Himalayas. He has also published many research articles in tectonic and quaternary geomorphology in the recent years. He has high scientific temper and strong HR relation in science world with high professional and managerial skills. He has edited many volumes in top-rated journals in the Elsevier and Springer publishers, and also the member of editorial board of Quarterly Science Advances and reviewer of many top-rated international journals in the science world. Sir, we are very delighted to have you here and would welcome you to start with your session. Thank you, sir. Sir, you are not audible.
Sir, your mic is muted.
Hello?
Yes,
Hello,
sir.
I'm audible now?
Yes, yes, sir.
Okay. So, good afternoon to everybody, and my special thanks to Madam Shruti Kangaji for giving me the opportunity to interact with you and discuss what I have learned from the different sources regarding the remote sensing and GIS applications in water resources. So, dear friends, I'm coming to my first slide. I think it's visual to you.
Yes, sir.
Yes,
Yes,
sir.
sir, but
Only
Okay,
requesting,
okay,
please, if
okay,
possible, slideshow mode. If
okay,
you can select
okay,
the
okay,
option, it
okay,
will be
okay.
more better for us.
Yes, so
Rest is fine.
remote sensing applications in water resources. So I'll quickly come to the slides, my slides number one. So as you have already studied, I think in this in 21 days remote sensing course that the remote sensing data since it started from 1972, which have a resolutions of 90 meter uh, and even 1 kilometer data has now reduced with a less than 1 meters of spatial resolutions. So the enhancement in the remote sensing technology has enabled us to do the more analysis, more scientific and accurate analysis regarding the water resources as well as the research regarding the geosciences and other worlds regarding the forest and ecology, climate change, and many more ways. So if you see in the first slides that since in the, right from 1988 when the India launched its first satellite which have a resolutions of 72.5 and average data which have a resolutions of 1 kilometer. So India reached the journey of in the Cartosat 2A uh, which have a resolutions of less than 1 meters. So this slide shows you how the sun synchronous satellites and how the resolutions of the data has enhanced right from 1 kilometer to less than 1 meter. So if you see the geostationary satellite series, so in the geostationary satellites also we have INSAT 1D and then now in 2016 onwards we have INSAT 3DR satellites which have a better resolutions and better capability which helps us to infer and interpret the data easily. So if you look at in the case of water security, which means the water resources research and what we are doing right now in the water resources since 1980. So the trends.
sorry to interrupt you, sir. Sir, your slide is not moving actually, and it's not in slideshow mode. Sir, please share entire screen so that.
Okay, okay. I think my slide is.
So please select entire screen so
Yeah,
that
yeah,
my
I
slide
have
can move.
selected it, but I think it's showing, it's moving, even though in. Just I'll again. Uh,
So please increase the percentage of the
yeah,
zooming.
yeah,
I think.
okay. Is it visible to you now? Hello?
Yes, yes, sir. Visible, but the zooming percentage is less, sir.
Zooming.
So the slides are very small, sir. We are not
Small.
able to see it, sir.
Okay. Yes.
So to increase the size, there is an option right down,
Okay, okay.
right side and down side.
I have enhanced that option, but I'll again share my slides. Once I'll click it, I'll again share.
Yes,
Okay.
sir. Yes.
Yes.
Yes, sir, it's in full screen now. Please unmute yourself, sir. You are muted. Yes, sir.
So in this satellite, in this particular presentations, I think it's in slide water security, which shows that when the satellite, when the India got its satellite data in 1988, right from 1972 when the America launched, the US launched its first satellite, which is known as Landsat 1. Now earlier it was
Slide is not visible.
okay. Slide is not visible.
Not visible.
Is visible now? Hello.
Not yet.
अजी, वो शेयर ही
No.
नहीं हुई है शायद, स्टॉप शेयरिंग हो गया था।
शेयर तो हुआ है। शेयर हुआ है?
हाँ अभी शेयर हो गया, बट वही छोटा वाला है। कोई बात नहीं, आप चलिए, वी विल सेंड यू दिस स्लाइड फॉर योर कन्वीनियंस।
Resolve my issue. Hello. It is
हेलो,
visible now. Full command.
सर दिख रहा है।
Okay. So in the 1980, it will discuss about the water security, that how the water science has evolved through the remote sensing. So in the 1980s, the trend was regarding the groundwater potential donations, that how the remote sensing and GIS enables us to prepare the groundwater potential donation map. Then in 1985, the snow melt runoff and forecasting glacial inventories. So with the passage of time, command area monitoring and reservoir sedimentations have become, then groundwater prospecting, mass balance studies, deep sea explorations, then irrigation infrastructures, and nowadays what we are doing here, water source assessment and monitoring. So these all things, like right from the groundwater potential donations to water resources assessment, management, and monitoring, we are all still doing using the remote sensing data. As remote sensing data has the capability to provide you the surface view, although we are able to know about the information about the below the surface of the earth by using the different parameters, uh, which you can say that the indirect parameters. From the indirect parameters, we are also able to know about the subsurface information, or you can say the subsurface water sources. So if we study about the water resources, there are three, four just slides which are just about the water sources right now. Then we'll see the applications of remote sensing and all these things. So as water resources are concerned, so water resources, we all know that these are the natural resources which have the potentially useful as for the water supplies, and 97% of the water on the earth's surface is salty water, and only 3% water is available as a fresh water on the surface of the earth, and only slightly two-thirds of these is frozen as in terms of glaciers as polarized. The remaining unfrozen water is found here as in small fractions below the ground, or I can say below the ground surface as well as above the surface, in form of um, reservoirs, rivers, as well as the major lakes which are found on the surface of the earth, and then certain portions of the water found below the surface of the earth, which is known as groundwater. So this is the water cycles, that how the water has been. I think everybody knows about this water cycle, which is known as global hydrological cycles, that evaporation takes place, then condensation and cloud formation and precipitation. Then somewhat portions of the water comes as a surface runoff, so which is the overland flow. Some water infiltrate into the subsurface, which is the inflow, or you can say the groundwater flow. So these surface and groundwater flow again reaches into the rivers and streams, then ultimately reaches to the oceans. So in such way, this systematic hydrological cycles we can able to present here. So this is also the part of the hydrological cycles. Here we have mentioned that the groundwater table. This is the surface water, the surface overland flow from the precipitation. Precipitation takes place in a snow covered area as well as in the planar surfaces, or you can say the area where snow cover not take place, and then certain water percolates. So some water here infiltrate below the surface of the earth, which act as a groundwater, and this imaginary dividing lines, which is mentioned here as this is the water table line. Above this portion, the area is known as unsaturated zone, and below this water table is known as saturated zones. Although we further subdivided this zone into the further three zones like soil water zones, then capillary intermediate and capillary fringe zones. The main difference between this water table, the zone lies above the water table and below the water table is that water which are found in this particular zone, here interspecies or you can say the pore species are partially filled with water and partially filled with air. Whereas the water which found below this water table are completely filled with water. All the interspecies are completely filled with water and there is no space for the air. So as I have told you that out of total water, only 2.5% or you can say 3% water occurs as a fresh water. Then the fresh water, 30% is groundwater, and then around 68.7% is glaciers and ice caps. Then in the this surface water, some water here as occurs as lakes, then rivers, then swamp and marshy lands, and soil moistures, and some water occurs as a ground and ice permafrost water. So this is the major subdivisions of the water which are found on the surface of the earth. We here generally studied the water into the three types: the water which are found on the surface water, groundwater, and frozen water. Means the water occurs in the form of snow and glaciers. So the surface water, as you already know, that surface water is water in form of lakes, rivers, freshwater, water, wetlands. Surface water is naturally replenished by precipitations and naturally lost through discharge through the oceans, evaporation, evapotranspirations, and groundwater recharge. Although the only natural input to any surface water system is the precipitations within its watershed. The total quantity of water is that the system at any given time is also dependent on many other factors. These factors include the storage capacity of your lakes, wetlands, and artificial reservoirs, the permeability of the soil beneath the surface of these storage bodies, the runoff characteristics of the land in the watershed, which again depends upon the terrain characterizations, then the time of precipitations and local evaporation rates. All these factors affects the proportions of the water loss. Then groundwater, as I have already told you that water which lies below the surface of the earth is called as the groundwater, and then groundwater it will vertically divide it into, then it is divided into the water which lies below the water table is the saturated zone, and water which lies above the water table is the unsaturated zones. So groundwater is fresh water located in the subsurface in pore spaces of soils and rocks. This is also water that is flowing within the aquifers below the water table. Sometimes it is useful to make a distinction between groundwater that is closely associated with the surface water and deep groundwater in terms of aquifers, which is sometimes also called as fossil water, connate waters, and different terminology have been used regarding the water which lies below the surface of the earth. Then third water is the frozen water, or you can the snow or glaciers. Several schemes have been proposed to make use of iceberg as a water source. However, to date, only few things have been done for this purpose. Glacier runoff is considered to be the surface water in the Himalayas, which is also known as the third pole of the world, or you can say the roof of the world, contains some of the most extensive and rough highlands areas on Earth, as well as the greatest areas of glaciers and permafrost outside of the poles. Tens of the Asia's largest rivers flows from there, and which provides food to a billion people which are depending upon these rivers. And the major rivers which are originating in the Indian portion is the Indus, Ganga, and Brahmaputra. So this we have already seen. So if you see here as the satellite data, which is the WIPS data, which has a resolution of 156 meters. So you can see here that these portions which have a reddish tone. So this reddish tone is basically the portions and certain portions of the Indus River basins, and then here you are Ganga flows, and then here we have a Brahmaputra. The white portion is this one white portion is the glacier or the permafrost regions or the frozen regions of India. So it will enhance it. Then this is 72.5 meter resolution, then 23-meter resolution, then this data is 5.8 meters resolution. So based on the resolutions of the data, we are able to interpret more accurately, and more advanced techniques are nowadays found to get the better resolutions data. So this is the average data. If you look the small cap of the average data, so we are unable to see here the more information. Average is 56 meter resolutions. Earlier one was WIPS. This one is the advanced WIPS. So this has a 56 meter resolution. Then list 3. This is the FCC, means false color composite, which have a 23.5, or you can say around some of 24 meter resolutions data. And then you have a 5.8 meters of resolutions data. So this 5.8 meters of resolutions data, we are able to interpret here the better information about the water resources as well as the other features which lies on the surface of the earth. So important thing is that if you have a better resolutions data, we can get the more information. Regarding the water resources study, we generally prefer 5.8 to 10 meter resolutions data. This data is enough to accurately measure the water resources on the surface of the earth, whereas for the glacier studies, we are now also using the on-screen Google data, which have resolutions of around less than 1 meters. So that data can also be used. But preferably we use the resolutions right from 1 meter to 10 meters of resolution is sufficient for measuring and accurately measure the water resources on the surface of the earth. So this is the area regarding the agriculture water management. So list 4 data we have digitized here the canals of the Jammu regions. This is one particular canal, and here these are the distributaries of the canals in the plain area. This portion belongs to the Pakistan. Basically, this is the international water which is mentioned in the yellowish line. So this is the Tavi River. So we'll see in the satellite data, even though you have already studied it, I think so, that in the satellite data, the water bodies appears in the cyan color. So this river body appears as a cyan color. So in the same way, we have also mentioned here that canal rivers measure using the resource set list 4, which have a 23.5 meter resolutions, and same here for the 23.5 meter resolutions for the Kharif seasons in 2011 as well as in the 2000. So for the water erosion studies as well as soil erosions, we can also use this satellites data. Remote sensing is quite useful, even though the small patches we are seeing here the greenery, and with the passage of time, here erosions have been taking place. So you will not find any red patches because if you have studied this remote sensing, so in the remote sensing, the green bands, or you can say anything which is green on the surface, in the remote sensing FCC data, it appears red. So with the passage of time, you are seeing here that reddish patch have been removed here, so it appears cyan in color. So seen here, so it changes with the passage of time. So in the same way, we are able to measure accurately the water erosion, that due to water erosion, how much sheet, drill or soil erosions having taken place. So this is the particularly watershed of the Jammu Himalayan region, which is known as the Basantar watershed. So we have marked it on the Google image. So you can see that this is the watershed of particular region. From this watershed, through the remote sensing, we are able to see or locate the accurate water bodies. So this is again the watershed, or you can see the clip of the watershed. So we are able to see or monitor here how the rivers have been moving. So such kinds of geomorphological studies can also be done with the help of satellite data regarding the river morphology, the channels, river behaviors, membranes, and all these things can also be done with the help of small scale studies regarding the watershed. So there is a one dam here in this location, so we are able to get the exact informations, and then we are able to map and match all these things. So this is one lake in the Jammu region. So I have just made such kind of study regarding the lakes, and then samplings have been made regarding the Jammu Himalayan region. So this is the Surinsar lake in the Jammu Himalaya. So one study regarding the surface water resources I have done regarding the Ravi basins. So this is the area of the Ravi basins. So if you are seeing, this is the Ravi rivers, and then one another tributaries joining it, which is known as the Oj river. So this is the dam, which is known as the digital elevation models map. Overlaid, we have overlaid here the drainage, or even the major river portions of the Ravi basins. So how these water sources or surface water applications now starts here right now. So and then what are the different applications? How the remote sensing is
Excuse me,
useful?
sir. Your slides are not moving. It's fixed on the second slide itself.
Oh, it's showing now.
हाँ अभी है.
Oh, okay. So this is the Ravi basin. Okay. So this is the digital elevation model of the Ravi basin. And in the Ravi basin, there are two major rivers. One is Ravi, another is Uj. So we have prepared this the land use, land cover map of the Ravi basins, and then there are certain indices which are we are able to determine from the Landsat data, any kinds of optical data, by just subtracting and adding the bands. We are able to know about the normalized difference moisture index. So this is what the moisture index. If you will see that the normalized difference moisture index, which enables us the crop water stress level, and is calculated as the ratio between the difference and the sum of the reflected radiations in the near infrared and short wave infrared regions. So based on this, we have identified based on the Landsat data. So we are able to accurately measure here the moisture index. So you are seeing here that low moisture is found in the hilly terrain, whereas high moisture is found in this image is belongs to the summer season. So or you can say the spring season. So during the spring season, moisture is very much high in this particular area, and low moisture is found in the hilly areas. Whereas very high moisture is found in the area which have a glaciated region. So these are the glaciated region. That's why it is showing very high moisture. So remote sensing also helps us know about the moisture index. So directly by using this equation, we are able to determine the moisture index. Then the normalized difference water index. So this water index for water body mappings, we are able to determine this moisture index. So high moisture, so you can see that high moisture is found in the rivers. So these are all different rivers, and very high moisture in the hilly area or in the glaciated regions. So this we also can accurately measure.
Excuse me, sir. Sorry, sir, I'm not able to see the next slides.
Sir, can you share your slides with us? We'll be sharing it from our end.
Right.
It feels that there is difficulty from your
Okay,
end.
shall I share now or after the completion of my lecture?
If you can share in WhatsApp to Shruti, we'll be directly sharing it within 1 minute.
Okay,
If you've got a good internet speed, we have got a good internet
okay,
speed,
okay,
and it share to me
okay.
also to Doctor
Okay,
Suraj.
I'm just sending my PPT to Dr. Suraj. You please share it with your all the participants. Then I'll come to this particular slide.
Okay, because otherwise
Yeah, yeah.
the students, because they are habitual in seeing, because the world has changed.
Okay,
Nobody wants to go without seeing a lecture.
okay,
That
okay, okay. I'm sharing right now. Okay, Surajji, I have shared my slides with you.
okay, okay,
So now you can send to the participants.
okay.
Even though,
And what I'll do is, what I can do is, can I share it from my end? If
yeah,
right
sure,
now I have
you can
not
share it. No issue.
shared, emailed you, have emailed you.
Yeah.
Yeah, I'm just downloading it, and I'll be sharing from my end. You just say next. I'll be doing it next.
Okay, okay, okay,
I'll be sharing it from my end.
okay.
Okay, so give me 1 minute. I'm just downloading it. I'm downloaded. Now I'll be sharing. So stop sharing it. We'll be sharing it from our side. You please stop share. Option D selected. You please deselect. Stop
Okay.
sharing it.
Please.
Slides
Next,
बताइएगा
next,
कौन
next,
सा?
next. Yes, but please stop. So, as I told you that there is also another index regarding the water, which is known as normalized difference water index. This is the most appropriate index for water body mapping. Body has strong absorbability and low radiation emitting from visible to near infrared. So if we look at here at this particular portions, we will see here that very high NDWI values. So this is reservoir. So reservoir showing it a very high values, and these portions, these hilly portions, or you can say the portions, this part of the Himachal Pradesh are the snow covered area. So in the snow covered area, the moisture index is also very high, water index is very much high. So by this way, we are able to get the normalized difference water index. So this is NDWI, green minus near infrared slash upon green plus NIR. So based on this, we are able to determine the reservoirs or the major water bodies, even though the snow covered area. So this normalized difference water index can be used or applied for this. Next, please. So you can see our paper. This is the part of our published publications. So you can see our paper. So if you look at the groundwater explorations, that how remote sensing is useful for the groundwater explorations. So this is the FCC data for our groundwater exploration and recharge. So this image, this particular image is from the southern India in the part of Hyderabad city. So we will see here that the low reflection, that absorption, this is also the surface water bodies. These are the surface water bodies. This is also the surface water bodies. So if we look at the satellite image that we are looking at in the particular, in the linear features, there is a red colors. So these red colors are vegetation. So this is basically the highly fractured area, and rocks are igneous, or you can say the crystalline nature. In the crystalline nature, due to crustal deformations and different tectonic activities, such lineaments and faults have been developed. When these faults have been developed, so these are the breaker zone. So water, due to the passage of time, the erosions and weathering have been taken place in this area. So because of the loose material are available in this area, so whenever there is a small amount of rainfall, so all the water from this area, even though this wide portion of land, intercepts here and infiltrate into these cracks. So you can say that the vegetation is very much higher in this particular lineaments as compared to the surrounding area. This means that these area have a high availability of water as compared to the other area. So you can see here that these portions don't have any vegetation. This means moisture index is very much less. So if there is no moisture, no water, so no vegetation. So vegetation also occurs in the area where you have a moisture content. So moisture availability is higher in the particular regions, or you can say in the particular patterns, in the linear patterns. So these are various for groundwater movements. So these are dolomites, dikes, which acts here as a aquifers. So water, there is no water, and waters are unable to pass through that area. So these are the barriers. So these are the conducts which for movements of groundwater. So from this area, the water moves. So this is a particular fault in this area. So from the fault area, water moves here. So and this surface water body. So all these things we are able to get from the remote sensing data. So remote sensing data helps us to know that how the water and where the water is available on the surface of the earth, and from the indirect parameters. Okay, from the indirect parameters, that right from the vegetation we are able to know that whether on the below the surface of the earth water is available or not. So water availability below the surface of the earth is depend upon the many factors, which may be the terrain characterization, whether there is a area is flat area, plain area, what is the quality of soil, what is the lithology of the rocks. So all these important factors are also we able to determine based on the satellites data. So from the satellite data, we are able to get the information on the surface, and some through some parameters, we are also able to know whether the water is available on below the surface of the earth or not. Next, please. So this is also IRS P6 satellite imaging showing the different hydrological features. So different features. These are the water body because absorption is very much high. So there is no reflection in the water bodies area. So different geomorphological features like denudation hills and granite species, habitations area. You can say the um, area where the population is there, then the paddy plains of granite. So fractured zone, these are the fractured zones. That's why the availability of water is there. So then dikes and paddy plains of granite and gneiss. So all these things we are able to determine from the remote sensing data. So remote sensing data also helps us know about the geological features, various kinds of rocks, vegetations, water bodies, even though the agriculture, crops, health, and agriculture crop patterns we are able to determine from the remote sensing. Next, please. So now I'm going to show again earlier what I have shown you that is related to the surface water, that how we are able to see or how we are able to analyze the surface water studies, whether it's NDWI, moisture index or water bodies index, then based on the digital elevations model, how the water moves. So all these things was the part of the surface water studies, whether the how the rivers are moving. We are even though able to know about the quality of the water from the remote sensing data. So this study we have done regarding the groundwater prospects mapping in the Jammu Himalaya. So this region we have taken. So this is the elevations map. I think you already all know about what is the elevations map or how we are able to determine this elevations map. This is basically the we have derived from the shutter radar topographic mission dam or various kinds of digital elevations model which you call as dam are available freely from the different sources in the USGS, even though various other downloading hubs provides now the satellites dam. So this is the geological map of this particular Jammu portions. So we have determined the different geological features, like different kinds of rocks. You are not aware of these kinds of geology of this particular area, but we have based on the satellite data interpretations, we are able to map such kinds of geological features in this particular area. Next, Surajit, please. So in this particular study, we have used what? We have used the satellite data, which is known as RSP6 in this particular case. Then some softwares, which is this ADAS imagine is the particular the image processing software. Then ArcGIS is GS-based analysis software. Then we have made some groundwater flow modeling studies, and then various kind. Okay, this is the basically the methodology we have used in this area. What we have done, we have taken the satellite data. In this particular study, we have taken the LIS4 data. I think you know that LIS4 have a resolutions of 23.5 meters. Then we have taken the shuttle radar topographic mission dam, which have a resolutions of 90 meters. Then topographic map, which is known as the topo sheets. Then soil map, which we have taken in our case from the Soil Bureau of India, which is nowadays known as National Bureau of Soil. It's located in the Nagpur. From that area, we have derived here the hydrological map. So from the satellite data, what we have derived here, we have made the visual interpretations and made the geology map, hydrogeomorphology map, land use land cover map, and structural map. This we have derived from the satellite data. And from the dam, which is in here as a SRTM dam, we have derived the slope map. Then from the topographic map, we have made the drainage map, and then we are able to generate as drainage density map. From the soil map, we, as I told you, that we have derived the hydrological soil texture map. Then by these all we derive from the satellite data. You can say that this portion have been derived from the satellite data, then from the topographic map, which is we got from the Survey of India topo sheet, and then soil. So here we reach here. So then certain data we have collected from the field, which is field. This particular research is field as well as remote sensing based research. So here we have collection of field data, then certain pre-monsoon water table. If you leave this portion, then pre-monsoon water table, post-monsoon water table map we have prepared. Then fluctuation, we measure the pre-monsoon water table in the field, post-monsoon water table, and then the fluctuation right from from post to subtract from post to pre. So we got the fluctuations map. Then all these layers we prepared using the these for this pre-monsoon and post-monsoon. We using the interpolations we prepare all these three maps: pre-monsoon map, post-monsoon water table map, and fluctuation map. three maps we have prepared in the GIS from the field collection data and three thematic layers have been prepared from here. These satellites based map, satellite database map, the geology map, hydrogeomorphology map, land use land cover map, structural map, soil map, hydrological texture map. So all these maps we integrate in the GIS. Then based on their application and based on their applications and their helpfulness to know about the water sources below the surface of the earth, we categorize them all these thematic layers. Then we have given the weightage based upon their importance to the groundwater occurrence, and then integrate all these thematic layers. We got the groundwater prospect zones, or we can say the groundwater potential zones map, that how much water or which area has the better availability of the groundwater resources below the surface of the earth. So if I'm stopping here for this particular slide. Next, Suriji, please. So these layers, what we have prepared earlier, these are known as the terrain characterizations layer, that hydrogeomorphology, slope, soil texture, land use, land cover, drainage density. Then certain parameters are known as aquifer parameters, like depth to water table means the from the just from the surface what is the level of the water. Then pre-monsoon water table map, post-monsoon water table map, then water table fluctuations map. These terms: discharge data, capacity, transmissibility, and hydraulic conductivity. These are related to the groundwater, and I think if someone have not studied, so they will not be aware of all these things. So if you look at the satellites data of the Jammu region, so here one river is flowing here, which is known as the Manawatari river. This is the mighty river, which is known as Chenab river. Then Jamutari river. So here small river is river and Basanta river. So on the whole, four major rivers are flowing to this area. So if you're looking at that, why I have not taken this portion? Because this portion belongs to the Pakistan. So this is the international water here. So we have made the analysis only for the Indian part. So next, Suraj, please. So as I told in the methodology that what we have prepared, so we have prepared this the hydrogeomorphology map. That what are the various features we are able to locate from the satellite data. We are able to map them. So we prepared here the different faults, then channel vars, that where we are able to locate the channel var, backspan, battlefield deposits. So different kinds of geomorphological features which we are able to analyze, interpret from the satellite data. We have prepared this particular map, which is known as hydrogeomorphology. So this is terrain characterizations layer number one. Next, please. So this is soil texture map. As I've told you that we have taken the soil texture map from the soil bureau from Nagpur. So based from that map, we digitize that map and prepare the soil textures. So we prepare this soil texture map. This legend shows us the recent soils, which means the soil which is found in the alluvial plains, or you can say the floodplain regions of the rivers. This is the Basanta river, this is the Tavi, this is Basanta, and the Chenab rivers. So then you have the slope map. This slope map we prepared from the SRTM dam. So you can see that very in the planar portions we don't have any high slope. So slope is 0 to 1%, then 1 to 3%, then 3 to 5%, 5 to 10. So maximum slope more than 35 is located just in the hilly area. So the general trends of the slope is towards the southwest. Next, please. So then we have prepared the land use land cover map. So based on the satellite data, in this particular case, we use here the list 4, which have a resolutions of 5.8 meter resolutions. So from the 5.8 meter resolutions, we have marked here the major settlement portions, which is mentioned here as a built-up area. So built-up, this is the Jammu city, so built-up area is very much high. Next, Surji, please. No, no, no. Back, please. Back. Yes. Back, back. Back another. So is it back, please? Back two slides. Yeah. Back one. Yes. So this land use land cover. Back, please. Next, yes. In the land use land cover layers, what we are getting here. So land use land cover also helps us to know that where the water will infiltrate, which is the area where we have a plainer land and agriculture land. So in the agriculture land, if there is an infiltration, so water table rest at a shallow level. If there is a settlement area, there is a low infiltration, the chances of shallow water is very less, water may available at the deeper levels. So settlement is may act here as a particular thematic layers which helps us to know that in which area the water availability is high or low. Next please. So this is the drainage density. Based on the drainage we have marked, even though nowadays we are mapping all these kinds of drainage from the directly from the SRTM dam. So but earlier what we have done in this particular case, that we mark all the drainage which are found on the topo sheets. We mark, digitized, then by using the interpolations map, we prepare the drainage density map. So drainage density is inverse function of permeability. The area where the drainage density is very much high, the permeability is very much low. The infiltration is very much low. So infiltration rate is high in the area where the drainage density is very much low. So the drainage density, the area where the drainage density is high, the infiltration is low. So high infiltration takes place in the planar area, or you can say the area which are the low lying in this particular case, which have a flat land, slope is very much low, so drainage density is low there and infiltration is high. Next please. So static water level. So as we have taken certain samples from the field data, so based on the sample we are able to measure here that this particular area have water level less than 10 meters below the surface of the earth, and in the hilly area we may have a water level more than 60 meters. And this particular colors, which is brown here, this portion act as a runoff zone because this is the mountainous region and we are unable to get any kinds of water sources, or you can say any kinds of water structure. So we are excluded this area. So we taken the area which is in these portions, right from 10 meter to 60 meter. This act as a runoff zone. So we have excluded this area for our particular study. So water table here is less than 10 meter, then 10 to 20 meter, 20 to 30 feet. So we divided the static water table of our study area into different zones here. Next, please. So fluctuations. So fluctuations, we have prepared here the fluctuation map from post-monsoon minus pre-monsoon water table. So this fluctuations map, then by using the interpolation analysis in the GIS, we prepared this thematic layer map. Next, please. So drawdown. Drawdown. So next, this kind of this drawdown, discharge, specific capacity, and hydraulic conductivity. These are specifically related to the groundwater hydrology. If you have not studied the groundwater hydrology, then we are unable to know about that how this discharge measure, then drawdown, specific capacity, and hydraulic conductivity measures. So next, please. Next. So these are the values of the transmissivity, hydraulic conductivity. We have also prepared, you can say that we prepared all these kinds of thematic layers. Next, please. So then what we do here, we integrate all these here. The delineation of GS-based groundwater potential based on the integration of different thematic layers considering the behavior with respect to groundwater control. That how these layers control the groundwater based on that. So what we have made identification of different evidential themes conversion of all these vector map into the raster map, which is known as the grid map, then assigning the weightage to different thematic maps. All these layers have been weighted into a proper manner right from 0 to 10. So based on their applications to groundwater of the particular themes, we have scored them. So assigning to score to the each individual class, then we integrated using the weighted index overlay method. So based on this method in the GS, we have overlaid all these layers. Next, please. So this overlay method, weighted overlay method, earlier it was known as weighted overlay method, but the exact term is weighted index overlay method, was adopted for combining the multi-class maps in the study area. This method is quite powerful as human judgment can be incorporated in the analysis. The weight represents the relative importance of the parameter vis-a-vis to the objective. So by combining all these layers, so what we have done, we have given weightage to the each and individual class of the particular themes. So right from here, structural hills. So if you can see that I have the hydrogeomorphology map. So I have classified the hydrogeomorphology map into the 10 or 12 parts. So in the structural hills, which is the hilly area, we have scored it 1. Okay, highly dissected, where there is a dissection in the structural hill, we have given a score 3. So if you see that the younger alluvial plains where the water availability is very much high, we have given it here 10. So the younger alluvial plains, river terraces, we have given here the 8. So point was 8, 9. So based on their applicability and applications, or you can say their importance to groundwater, where the water occurs. So based on that, we provide score to the individual classes. So in the same way also, we have given score to the different evidential themes like soil moisture, pre-monsoon water table, post-monsoon land use, land cover, slope, soil texture map. So in this particular area, discharge, drawdown, and specific capacity. So all these layers we given weightage, and then we plot all these things. Next, please. Next. So yes. So all these layers. So right from you can see here, this is slope, this is land use, land cover, then drainage density, hydrogeomorphology, geology, then water table maps. So we plot all these things and we will get here the groundwater potential variations map. So what we will get here, that the area, as we have seen in the satellite data also, that this area is the planar area. So in the planar area, which have a alluvial plains, or you can say younger and older alluvial plains. In this area, the water availability is very excellent. Good in the area which lies above, or you can say the northwest to the northeast to the this excellent zone. Then you have a moderate zone, low runoff, and runoff zone. So this area, what we have excluded for our research, so we have just keep it here as a runoff zone. So by clubbing all these evidental themes, we are able to get we get here the groundwater durations map. So water availability in this area is very much high, which is known as excellent zone, then good, moderate, and low. So this groundwater prospecting people are doing right from the 1980s to 2020. People are getting different ways for their particular study area, the groundwater potential duration. So in the groundwater studies or in the hydrogeological studies, the application of groundwater prospects is one of the most important, and most of the people who are doing research are going through all these kinds of studies regarding the groundwater prospect mapping. Some do the artificially recharged donations map. Some know about the site selections map, where we are able to get the sites for artificially recharged to groundwater. So various kinds of similar studies we are able to get from the integration analysis in the GIS by using remote sensing and GIS data. So this is also the groundwater potential donations map. Next, please. So this groundwater potential generations map, we can also validate it with the groundwater modeling also. So this is the conceptual models of our study area. That this is the hilly area which I have shown you the. So these are the groundwater modeling using mud flow. So different layers we are able to determine that area where we have a very high water tables, then we have a low water table. So in this way, groundwater modeling we have done, and the groundwater modeling numerical. Next, please. So this is next. So yes, from the groundwater modeling also we are able to delineate here the excellent, good, low, moderate, and model inactive zones. So based on the just for by using the aquifer parameters, and then we are able to know about that this particular portions have a very high prospects of groundwater, then we have a good prospect, then we have a moderate and low prospects of water. So our remote sensing study, we have validated it with the groundwater models. So mod flow based studies this. So this is the mod flow. This is our GIS based potential map. This is the model output map. This model is based on the groundwater modeling. So you can see that here, this is the GIS based. GIS shows that 30%, GIS shows 39% area as an excellent zone, whereas groundwater mod flow shows the 30%. So the trends is almost similar. So if you will see in the bar diagram, bar charts, so trends of analysis, trends of result regarding the GIS based, or you can say the remote sensing based GIS potential generation map, and mod flow based output are quite similar in nature, which we can say that the remote sensing is quite useful for groundwater prospect mapping. So now the frozen water. So first I have discussed the surface water, then I have second was the groundwater, and third is the frozen water. Or you can say the glaciers study, how we are able to do the glacier studies. So this basically this should back please. Back. नहीं पीछे कीजिए. Yes, please. Next, please. Yes, okay. So, yeah. Stop, please, stop. So, most of you have seen this very famous spectral curve that this is related to the water. So, right from 4 to 7, okay, 4 to 7 micrometers in wavelength. So, absorptions increases, then absorptions dip at 7 degree. So absorption is very much high in the 5, 6, and then reflection is higher in the 5, and then 6, and then in 7, there is no reflection, only the absorption takes place. So this is the spectral curves for the water. If you see here for the snow, ice, and vegetation, so see here, so for the snow cover, the reflection is very much high. In the water, reflection is very much low in the optical data. So, whereas in case of snow, the reflection is very much high. So, that's why water, or you can say the snow cover appears as bright, or you can say white in the satellite image in case of FCC in optical data. Up to here, if you see up to here, up to 0, right from 0.4 to 0.7 micrometer. So snow cover has a very high reflection as compared to the water. Water has a very poor reflection, and snow has a very high reflections. Snow means frozen ocean of water. Next, please. So, as I told you, that we are also able to know about the quality of the water. So, if you have a total solids, as you can say, the suspended solids are very much high in the water. So, spectral reflectance curves is very much sharp. If the water is pure, okay, there is no suspended solids found in the water, so curves is like this. So, based on the total solids, present in the water, the spectral reflectance curves behaves like this. So, based on the total solids, you can see that if you have a 200 milligrams per liters of total solids present in the water, so your spectra behaves like this way. This spectra we are able to determine from the any image processing software. Next, please, Surajit. Next, this is the same spectra for soil water. Yes, as I told you that the spectra for the snow in the optical regions. So if you see right from 0.4 to 1 up to 1 meter, so reflections for the snow cover is very much high. Even though in the clouds is also very much high, whereas in the thermal infrared portions, the clouds cover has a very high reflectance, whereas in case of snow, the reflections curve dips here from 1.5 to 2.5 micrometers. So that's why most of the study regarding the, or you can say the better study, we derive from the optical data, or you can say the data from 0.4 to 1.1 micrometers easily. So this is another reflectance curve which we have derived by using the same way what we have derived in the normalized difference moisture index or normalized difference water index. So this index is the normalized difference snow index is most common spectral indices which is used in the sphere and green for finding the snow covered area and non-snow covered area. So the which area you have a snow cover and which area you don't have any kinds of snow. So by using this particular ratio and DSI green minus sphere upon green plus sphere, we are able to determine that which area have a snow in the snow covered area. Even though in the satellite data, if you have an FCC of anyone, like Asters, like data from the Landsat series of Indian resources data or list data, so we are able to determine this NDSI. Even though from the models we can also try to this NDSI. So as the Surajit, please back up. Yes. So even though from the remote sensing data, we are also able to determine which area have fresh snow and which area have a old wet snow. So as the snow wet becomes old, so it becomes compacted. So the spectral curves like behaves like this. So fresh snow have a very high reflectance. So as the snowfall takes place, it has a very high reflectance. So old snow have a low reflectance in compare as compared to the fresh snow. So that's why we are able to determine such kinds of analysis that whether the snowfall having taken place right now or not. So such kinds of study can be made. So in case of NDSI, it is the ratio of 1 to minus 1 to plus 1. The higher value for the fresh snow is more than 50 and less for the old glacier snow is 0.35 to 45. So if there is fresh snow, the value of NDSI is more than 0.5. If the snow is old, the value is 0.35. Next, please. So one study we have made regarding the glaciers mappings, that how the glaciers moves over the period of time. So which is known as the glacier dynamic studies. I have chosen very small and very basic studies for you that how the remote sensing can be useful for the remote sensing. How the remote sensing can be used for the water resources studies as well as water resources means in terms of groundwater surface and frozen water. So next please. So this is one glacier in the Ladakh region of Jammu and Kashmir. So this is very famous glacier which is known as Machoi Glacier. So based on the list 23 meters data, list 3 which have a 23.5 meters of resolutions in the 1999, the glacier area is this. So this is the glacier area. This is the FCC data. Directly from the FCC, we are able to get, as I have told you, that snow reflectance is very much high in the optical data. So optical data shows that this portion has a snow cover. Next, please. So in the 2013, next, please. The snow covered dunes, and then in the 2017, the area reduces. Next, please. Okay, so based on the temporal analysis, we are able to measure that in the 2017, that snow cover has been reduced. In the 99, you are seeing looking here that the glacier boundaries this much. Okay, and in 1965 Toposhit, the area covered by the glacier is very much high. With the passage of time, glacier reduces and area also reduces. Next, please. So such kinds of temporal analysis we are making here. So average annual temperature maximum. So maximum temperatures in this particular region is increasing. So these are the data which we got from the Indian water portals right from 1900 to 2017. We have data, then we have extrapolated up to 2020. So we are to find the trends. So we are finding here that in this particular Majori region, that temperature is increasing, maximum temperature is increasing. So you are looking that the trends showing the increasing. Next, please. So minimum temperature is also increasing and precipitation is also increasing. So this means that snow cover reduces, means snowfall reduces, the liquid precipitation increases, whereas the soil precipitation decreases. Back please, Surajit, back now. So what happens? Liquid precipitation increases in this particular region, whereas soil precipitation decreases. That's why glacier area having reduced. Next, please. Okay. So as I have mentioned here that in 1965 the glacier area is 5.6 square kilometer. In the 99 it is 5.46. In 2013 it is 4.84, and in 2017 this we got at 4.92. So there may be chances that glacier may have increased, whereas maybe in 2017 there may be chances that snowfall heavily occur in the particular dates, why we have got the data. Otherwise, the trends is showing that the glaciers are reducing because minimum as well as maximum temperatures are increasing. So earlier the snowfall was taking place, snowfall was high. Now with the passage of time, the liquid precipitation, snowfall in terms of if we study in terms of precipitation means the liquid precipitation increases, soil precipitation decreases. So area of the glaciers are also increased. Whereas such kinds of temporal studies we have also find for the discharge of the river. So we have find from right from the 2000 to 2020 that in some rivers, the snow-fed rivers in the Jinskar Himalaya or in the Kashmir Himalaya, where the flow of the rivers or you can say the discharge of the river have also been increased from 2 to 7%. So some rivers have a 2% increase in their discharge, some rivers have a 7 up to 7% of increase in this discharge. Because of what? Because of in a very particular portion, in a very particular portions of the air, right in the summer where you have a precipitation, whereas the snow in the snow-fed area, the discharge has been reduced because the liquid, you can say the snow precipitations have been reduced over the period of time. So this is the particular study we have made to mention here the particular zone that which area we have the snout of the glacier. To mention here the snout of the glaciers, we have marked this line. Then there is another portions where we have a debris cover. This is the snout of the glacier. Up to here, the glacier, and then the water coming from the glacier. So this is the these portions have the snow cover. Next, please. Okay, so this is all about the today's presentation that how the glaciers, water sources which are found on the surface of the earth, as well as water which lies below the surface of the earth, how we measure and what are the different applications of water sources. Anyone have any questions regarding the glaciers,
Any
surface
question?
as well as the groundwater studies?
Anyone? Questionnaire? Any study? Any how to do it?
Even though many other kinds of modelings we can do from the glaciers, besides this, the remote sensing also nowadays providing the GRACE data. Based on the gravity analysis, we are also which have a very coarse resolutions nowadays, but we can also find that which area have a high water stress and which area have a low water stress. Whether the water is improving in the ground surface or not. So such kinds of studies can be done from the satellites data regarding the groundwater. So groundwater studies can nowadays be easily measured through the gravity recovery and climate experiment data, which is joint venture of NASA and German space agency. So they are providing the satellite data which can provide the groundwater information also. So we have also made such kinds of study. If you wish to know or study about the groundwater using remote sensing, you can see the grease-based analysis by using the different sensors. So such kinds of 4 to 5 studies and which are also published now are available in my Google Scholars, so you can get from there. Anyone who wish to ask me anything, even though we have not interacted and made any kinds of introductions with you. So anyone who wish to ask
Good
me?
afternoon, sir.
Okay, yes, good afternoon.
Sir, Anshul this side.
Okay. So
Can you elaborate more about, sir, pre-monsoon and post-monsoon field investigation data?
So pre-monsoon means this data we have taken during the summer season. So we just based on the samples, how we collect the sample basically. So based on the measuring tape, we go to the dug well and measure the level of the water. So if your dug well have a 8 meters water below the surface, this means the level of the water is 8 meters. So this is one entry. So same way we go to the field and collect the level of the water. So this is for the pre-monsoon. So pre-monsoon we usually take during the summer season. Okay. So as far as the post-monsoon is concerned, when there is a monsoon, so after the monsoon, okay, post-monsoon means after the monsoon, when the monsoon ends, during the northern India, it is around the October to November. In the October to month of November, we go to the monsoon in the stream belt and we collect the data, and then we'll find that during the pre-monsoon, or you can say in the summer season, because of high pressure on the well, okay, for the groundwater application uses in domestic irrigation and as well as in the industrial purposes, the water generally dip into the deeper level, and after the monsoon, when there is a recharge, is heavy recharge because of monsoon, water tables and the water tables in the wells also generally acts at a very shallow depth. So we, by this way, we are able to measure the pre-monsoon water table and post-monsoon water table. So by subtracting from post-monsoon to pre-monsoon, so we get the fluctuation, that how much fluctuation having taken place over the period of 2 periods, that is pre-monsoon and post-monsoon. So this is the way we are able to get the information about the pre-monsoon and post-monsoon. Then what we'll do, we use the interpolation analysis. Then we'll add all this data in the Excel sheets and integrate in the GIS. Then by using the interpolations method, we prepare the map regarding the pre-monsoon, post-monsoon, or many other kinds of map. Even though you can also do such kinds of interpolation analysis for the groundwater quality. We have also published many publications regarding the groundwater quality, where which area you have a good quality of water, which area you have a poor quality of water, even though the groundwater potential index we have determined. So all these kinds of studies, which is very basics in the remote sensing and GIS regarding the interpolation analysis by adding any kinds of data. So such kinds of analysis we can easily done.
Okay, sir. Thank you. Thank you so much, sir.
Okay.
Any other question? I seem perhaps there is no question left. So I'd like to thank Dr. Ajay Kumar Karu from Jammu University that from his busy schedule he has came up and he has enlightened us from the basic to the advanced technique of remote sensing and GS. And I will also request, because there is a lot of student saying about the appraising your presentation style, so we'll like to have one more lecture from you in coming days, because you've got a lot of quality publications in high reputed impact factor journals that will be a advantage, and the students will be benefited from your knowledge. So it's my personal request that please do accept our invitation for the coming lectures. And today it was an extraordinary, outstanding presentation, a refreshing course, because whenever we are saying that DST has given a refresher course, so for us also as an individual, as a researcher, we also enjoy seeing reminds us about the earlier research what we have done and how we can frame our future research. So that was a great 1.5 hours of presentation. And with this, we conclude today our first session. And thanks, Dr. Ajay, once again.
Thank you.
Thanks a
Thank
lot.
you, Dr. Suresh, for such a nice words. Besides this, I also thanks to the participants for patiently listening. Although there was some problem regarding to moving the slides ahead. So thank you once again. Thank you.
Thank you.
Thank you, sir.
Thank you.
Bye.
We'll again meet today at 2:30, because we have got extended session. So we'll start our new practical session from 2:30 onwards. So please do join at 2:30, and by then you can have your lunch, whatever you want, and we'll meet again at 2:30. Thanks a lot. Bye bye.